In computer science, we have a very important topic called computer networks. So we are going to follow a very good book from Tanenbaum, Femster and Weatherall. And the content I have taken is just for educational purpose. The copyright is with the authors and the publisher. So let us start with the chapter number 1, which is the introduction. We will talk about various topics because all the introductory part is here. If you go back to history, what we see in past 3 centuries, there were some path-breaking technologies. If I take you to 18th century, it was all about industrial revolution. We saw great mechanical systems. It was all about the industries like the cotton, textile, all these industries came up. Then there was another very important technology called steam engine in the 19th century. And then came the computers. This is the first computer I'm talking about, ENIAC, 20th century. And the whole idea was information, data gathering, processing, and distribution. So the computer will work on some data. So how to gather it, how to process it, and to distribute it. This was the new technologies, and the way to do all these things has come up in 20th century and still ongoing. Along with this, there were various developments which we need to talk about, like the telephone networks, invention of the radios and the televisions, and then the computer, the extraordinary, the unprecedented growth of computer science, computer industry. It was exponential. The satellites were made, launched, communication satellite, the Earth observation satellite, and then came the internet. So, because the things have changed now, the ability of the systems and the individual to gather, process, and distribute the data or the information, it has grown over the years. So we have all the data-centric things, so we need some sophisticated information processing. This is in demand. That is why as the ability grows, the processing techniques grows. Uses of computer networks. As I said, computer industries has taken an exponential curve growth. And when this computer science, computers, that is the computing devices, they came up with communication, to talk, to communicate, to send, to receive. Now, when this communication combined with or aggregated with computers, the computer system, how they are made, has changed. Previously, when single computer used to work, or we used to work on a single computer, now the things have changed. The organizational, institutional, computational needs have changed. And now we have multiple computers with high computing powers. They are interconnected. Now the computers are interconnected, and these systems of interconnected computers are called as computer networks. So computer network is a collection, is an interconnection of autonomous computing devices. So first thing is they need to be interconnected. Second thing, they are autonomous computing devices. I'm talking about your laptop. I'm talking about your smartphone. I'm talking about the electronic gadgets at your home. So this is computer network. Now when computers are connected, say 2 computers are interconnected, they can exchange the information, the data. They can send, they can receive. How do they do it? There has to be some transmission media. Nowadays, we don't see we don't see wires. All are wireless. But the still technologies which are there, the transmission take place through media copper wire. This is the transmission media. The fiber optic cable, the radio waves. We use microwave, infrared. Communication satellites are also there as a mean of transmission media. So networks are basically connected to make larger networks. And the networks of network is called the internet. The internet is network of network, internetworking. So I am making one more network and I'm combining this with the earlier network I made. This is the networks, internet. Now, whenever we talk about a computing device, we have to talk about the data, information. So whenever we go to a web browser, say Google, Chrome, then we just type what we want and we get linked to various websites. We can go to various social media sites. So now the way of accessing information is quite easy. You have mobiles in your hand, smartphones in your hand. We have mobile apps. Now this can also access some remote information anywhere in the globe. New establishment, new organization, they are actually starting online. Okay, if you want to have a taxi, book taxi, you need Ola, Uber. Now if you want to book some food, get some food on your doorstep, you'll do Food Panda or say, Save Hunger or Swiggy. Even the information, which is very important, the news, as the news has become online, it has gone to various audiences, large and broader audiences. Now you see TV on the news on the television. The more the news is on the internet, that is the YouTube. The channel have now migrated to YouTube because this is an online platform. Even the online publishing, the social media platforms like the e-commerce website, online publishing, they are doing the work because they are giving you notifications on your behavior. If you go to e-commerce and type something, content will come again on your browser or somewhere. Right? The online digital libraries, like the ACMs and the IEEE computer societies, they are putting their journals and the conference proceedings online. So you are able to know what is happening, every one of us. And most of the internet information accessing is done through a model called a client-server model. A client-server model. So client and a server. As the name suggests, client will explicitly ask for something, some information from server. Server being the dominating one, it will honor the request, return the request. So this is a picture of two clients using the computer network to ask server to access information, to get the information. So how does it work? The client-server model. This is the widely used and this is the basis of various other network usage. I can give you an example of that. Computer science has developed. So we have the web application. This is the most popular realization of client-server model, the web application. So how does it work? You might have seen your web application, web apps. Now here, when the web app request it as a client, then the web pages which are on the server, it will be generated. The web, you are on a browser and the web pages may be in the database that will be responded to the client request. So client will ask the server will get it from the database and will respond to you. So client-server model is not just in a building, it is applicable even to opposite corners of the globe. So if you are in India and there is a server or in Los Angeles, then also you can get the information. For example, a person at home, it is accessing a page through World Wide Web, www, the internet, or the remote web server. And the person is sitting at his home, the client. So a server can handle multiple thousands and lakhs of clients simultaneously. Previously, previously when it was conceived and was being made, the clients were limited. Now we have thousands and thousands of clients which are requesting from the server. And there are many servers also. So how does it work? How does it work? In a client-server model, there are two processes. I will talk about TCP, UDP, all those connections in the later discussions. But here, to be as a naive user, we need to understand there are two processes. One is running on the client, one is running on the server machine or a computing device. So client process on the client machine, server process on the server machine. Now, how does the communication take place? The client process is going to send a message using the network to the server process. So these are actually the computer programs. So these are communicating. So client is sending a request. Now client will wait because it has sent a message. Now it will wait for the reply message. So now the server, whenever it gets the message, it will reply to the request from the client. So the reply will be sent back to the client. So this is how the communication works. Client requests, server responds. Client requests, server responds. Now, another model, because we just talked about the client server, there is another model for accessing information. This is peer-to-peer communication. Peer is your friend, the person who is sitting with you or working with you. So peer-to-peer, peer is actually that, the term meaning is that. Now, this individuals, they form a loose group and they communicate with one another in the group. As you see here in the picture, one person can talk to another person, one person can talk to multiple persons. So there is no fixed division here as client and server. So client and server is not fixed here. There is no fixed division here. I'll give an example of BitTorrent. This is also a peer-to-peer system. So we don't have a central database of content. Each user is going to maintain its own local database of content. That is very important. Each user has its own local database of content. Now, whenever a new user will come, what he will do? Because the data, there is no central database. A new user can see for the existing member what he has. And this will iteratively go on. That is, this looking up of from a new user, repeated indefinitely, will build a large local database. For example, sharing of music, sharing of videos. This is why peer-to-peer communication is normally used. But I'll give you an example of Napster. What happened around 2000? Napster became so popular because it was all about sharing music and videos. Because of the copyright infringement, it was taken down. Napster was shut down. And let me tell you, the most popular internet application, which is your email, you are using it on daily basis worldwide. If you go conceptually, this is also peer-to-peer. Popular internet application, email. So person-to-person communication, when we go to 19th century, it's all about telephones. So you can relate it today that person-to-person communication is equivalent to calling on telephone. So email, what you use, you can now attach audio, video, text, pictures on an email. So this is person-to-person communication. And various internet users, they are using instant messaging. For example, you use Line, you use WhatsApp, you use Facebook Messenger. So this has come from a basic program called the Unix Talk program. Around 1970 it was. And here, two people can chat, can talk, can type message, get message on real time. This was derived from the Unix Talk program. Now, multi-purpose messaging services like the micro blogging sites, Twitter sites. Here, people can send short messages around 140 characters is given, and these are called tweets. And these tweets will be shared across the globe with all your followers. This is also a kind of person-to-person. The internet application. Here we have audio, we have video. Audio can be, streaming music like the Spotify or Ghana.com. Video is Netflix, Amazon Prime. YouTube is also this comes under this category. And Zoom, we have Google Team or Microsoft Team, or they are very important for distance learning, even for the geographically challenged people. Those people who are living or staying at remote area, they can get benefited by it. So between this person-to-person communication and between this accessing information, there is one more application called the social network. So person-to-person and accessing information, there in between we have one more applications, a set of applications, social network. For example, Orkut came, then Facebook came. Facebook is now everywhere. So here Facebook, basically it was made to connect to friends. Now you can create, update person profiles, you can do business, you are becoming popular on Facebook. This is the way of social media. Then we have Wiki. This is a collaborative website. Here, people of a community can edit, can read, can work on it. This is Wiki. So I'll tell you about the most famous free encyclopedia, which is called Wikipedia. Now you get exact information, logical information, relevant information on Wikipedia. Electronic commerce is everywhere. You do online shopping. This is already popular. So there are thousands of companies offering millions of products. and you can just shop it and shop and get it at your doorstep. You are paying bills, you are managing your bank accounts, you are managing your investments, all using e-commerce, financial technology, fintech. Now you can transfer money with your friends, with other people. And one more industry, which is a massive industry, is online auctions for these used goods, second-hand goods. So this has come up as a massive industry. But unlike this traditional e-commerce, e-commerce is basically a client-server model. E-commerce is based on client-server model. But the online auctions we are talking about, they are peer-to-peer. Why? Because once you do online auction, say if you are a seller, you are selling something, but you will be buying something also. So at the same time, you are a buyer, you are a seller also. So it's a kind of peer-to-peer. But let me tell you, we still have a central server in the peer-to-peer in this case, and the database is going to hold the products for sale. Now this numeral 2 and TO, this sounds equivalent. So that is how some name has come up, and these are being used widely in the industry, namely in e-commerce. So these are Q-related tags 2 and 2. So business to customer, B2C. So business to consumer. So if you want to order online, you are a consumer and the business is the publisher. Business to business, B2B. If you're a car manufacturer, you are asking for, say, a car tire, then you are doing business to business. Government to business, government to consumer, G2C. Now if the government is distributing the text form, that is government to consumer. Consumer to consumer, online auction, consumer to consumer, the company and the tire company. P2P, peer-to-peer, we talked about music or file sharing, Skype. Entertainment. Now we are entertained everywhere. Flight, on your laptop, on your mobile. So now you can find and buy and download the songs, the movie, high definition, ultra high definition. Television has changed. Now because the television is now based on IP technology, IPTV. Rather than having those cable TV and radio transmission, now you have IPTV. And especially the internet radio stations, now you can watch your favorite TV shows or movies. For example, you are watching the Money Heist, you are watching the Squid Games, all and multiple times. In a single house, your brother, your sister, your mother, your father, everybody is using device, everyone is watching something, and this is all going via a wireless network. That is how the network come here. There are new movies which are interactive. That is, at every point they are going to ask, tell us what to do. That is, if somebody is dying, if you want to save them, you can save them. So they are creating alternate scenarios. All the cases are there with us. This is how the entertainment world has changed. Live television is interactive. Live television, they are quiz shows. You can participate. You can choose the contestant. You can vote for them. So I was talking about this IPTV, and this feature is very important because, you know, the online game industry or the gaming industry, for example, the virtual dungeons and the simulators, they have gained immense, say, popularity. In the virtual world, it is providing us as a persistent setting. Now the user can experience on 3D. The Internet of Things. So this Internet of Things is very important because you know it. Mark Weiser. So he came up with the concept in 1991, ubiquitous computing. So he said this will be computing, will be computers, will be everywhere. So today we have security systems, we know the door and window sensors, every one of us has it. The smart electricity, gas, water meters, they will tell you what is the usage. There are smoke detectors. It can directly call the fire department, not just beeping. It is going to call the fire department. There are smart refrigerator. It will tell you that your milk is about to finish. So this all, we call them as Internet of Things. This is a revolution. This is all about connecting every electronic device which we buy to the internet. Now we have high-end cameras. They can just send photos, like the photographers. They send the photographs to the editors online. You can just have television, like, these are multiple things you can see on your mobile television. Power line networks. You know how much water you have used. Or even if you are taking bath, it will tell you the ladder is up. Please go down. Or just manage it. Even the report of environmental monitoring. These are the applications that can help you save the bill. Global warming. All these will help you in countering it. This is the Internet of Things. Every device is now connected, giving information. Types of computer networks. So we will be talking about various computer networks, but the distinct types of computer networks, let us start with that. You will find it in an enterprise, in a home, or even in the vicinity, your neighborhood. So to access internet, these networks are called as mobile and broadband access networks. To access internet means data, to connect to the internet and get the data. Then the data center networks. Here we have data housed and the application. Then we have the transit networks. Transit means if you are going from source to destination and you are staying somewhere, or in between you are waiting for some time, that is called transit. So this kind of transit networks we'll talk about. And then we have the enterprise network. It can be your campus, your college, your institution, your building, or organization. So here we will see the enterprise networks. So we'll talk about one by one, each of them. Broadband access networks. Now most of you might be having this network at your home to access the internet. Previously, when they became popular, people were buying the computers for word processing, games, etc. But now you'll find some people are buying computers only for internet access. So internet access, why it is important, it is providing you, that you are inside your home and you are now connected to whole globe, whole world. So here you can, from your comfort of your home, you can access information, communicate to people, make friends, buy products, buy even these services. Now here is Mr. Bob Metcalfe. Now he is the inventor of Ethernet. I'll tell you about this. IEEE, it is a standard. But for now, he said something. Actually, he hypothesized. He postulated something. And he said that the idea of a network, value of a network, the respect of a network, or the size of the network is proportional to the square of the number of users. So what are the number of users? Square it. That will tell you the size or the value of the network. And whatever he said, actually it is called as Metcalfe's hypothesis. And because of this, now you see his thoughts are so prominent. The internet comes with that size that he postulated. So you see how internet has evolved from Metcalfe's hypothesis. So broadband access network, they are multiplying, that is, people are using it. So they are delivered to your homes through various transmission media like copper wires, telephone lines, coaxial cable like the cables, and the optical fibers. And the speeds are tremendous, more than gigabit per second, and mostly people are using it on mobile now, because mobiles are almost like computers now. Mobile and wireless access network. Now these are two different things. Mobile network and wireless access network. They are two different things, okay? So mobile computers like your laptop, tablet, smartphones. This is the largest, fastest growing segment in the computer industry. Most of the, say cost, time, the effort is put in these, and people are buying it because. So people use their mobile devices, these tablets and laptops, smartphones. So they are using it anywhere. This is very important. They are moving and using. They are reading, sending email. They are in Twitter, they are tweeting, they are watching movies, they are listening to music, they are playing game, they are going from here and there through maps, or simply surfing. Now, the interest is where? In car, in boats, in airplanes, it is impossible to have a wired connection because the airplane is moving always. It is in, thousands of feet height. Cars, boat. Now, what about cellular networks? This is a familiar kind of wireless. See, cellular network means you have a mobile. You must be paying some company for that mobile connection. So that is the easiest kind of wireless I can tell you right now. And what about wireless access networks? Wireless hotspots. I hope you got the idea. Mobile is different. Mobile is the company you are paying, mobile network you are getting. I am talking about wireless hotspot, and there are various standards of 802.11 IEEE standards of wireless LANs, WLAN. So it's all started, 802.11a. Now we have 802.11ax. Next is also coming. So from 54 Mbps, now we have gone up to 10 to 12 Gbps. So I'm talking about wireless hotspot based on 802.11 standards. And here we have wireless network. This is a wireless network standard for mobile computers and portable devices. You can take your phone and get the data connection from the hotspots, and of course the tablets also can have. For example, they are helpful for the services like Uber. It is not Uber, it's Uber, Ola, Lyft, like. So please remember, let me tell you again, wireless networking and mobile are not identical. They are different. Let me tell you a tabular, way to understand this. Wireless networking and mobile. Mobile is what the company you are connected with. Wireless networking is networking with wireless, you're getting data. So let's just take an example of desktop computer in your offices. They are neither wireless nor mobile because they are desktop computers. A laptop computer, if you use it in a hotel room, so it is wireless? No. You have to put some wire into some jack. But it is mobile. Okay. Because laptop is, of course, you have taken from your house to your hotel. Then when networks in an unwired building, a building where is no wire, there are networks, so it is wireless. But it is not mobile. If you go out of the range, you won't get the connection. But store inventory with a handheld computer is both of them. You can also tell this in another way, that wireless computers are not mobile. If you go out of the range, it won't work like a mobile, a cellular network. So I'll tell you an example. Office, home, if it is there and you don't have proper cabling. So what we can do? We can have the computers which can be connected wirelessly. Rather than installing wires, we can do this. So there are also true mobiles. Means as those application, there are mobile and wireless application both. They are also like that. I'll give an example. See, there is an airport, a car comes here, then return back, and now a person has to charge. That what is the cost of parking and everything. So now this car rental return clerk working in a parking lot, he is having a wireless mobile computer. So mobile also and wireless also. So for example, he is scanning the barcodes or the RFIDs in the returning cards. We have FASTag in India. So their mobile device, they have built-in computer. They have a connection with the main computer. They can get the rental information, amount information, what they have to pay, and they can also print out the bill also. So it is mobile also, wireless also. The smartphones which we have, it can be Apple, it can be Samsung, it can be Vivo. Now these combine the aspect of both of these, mobile and wireless. So you have mobile phones also and mobile computers. It is acting as mobile phone and mobile computers because now we have an operating system. When you are using data, when you are calling someone, that is you are using mobile services. When you are using the data with some certain network, access network, you are using the data with the access network. So these phones connect to wireless hotspot. They can also automatically switch between networks like 3G, 4G, some Vodafone, some other mobile service. So previously, when there was no internet data, etc., it was all about SMS, short messaging service. In US it is called. In other places also it is called. In US it is called as texting, text messaging. So this was used tremendously when data was not that popular, and it was not that inexpensive. Right now we have, but now because of WhatsApp, Signal, Facebook Messenger, these all have overtaken SMS. Now people don't SMS or they don't text like this. They just use these apps to connect. In this mobile and wireless access networks, see, your mobile is having now a GPS, most of the mobile, global positioning system. In the Navstar GPS which US provide, there are around 24 satellites, around 800-900 kilometers above. And they are using the process of trilateration to actually point the location, and you can get exact location and the height also sometimes. So exactly location can be known. So what are the good candidates? For example, you want to eat Chinese. You want to know what are the Chinese restaurants near me. You want to have local weather forecast. You are taking photographs and video. You want to annotate it or name it with some georeferencing tags. So this is geo tags. So these are all the popularity and usage of GPS on your mobile. Then because mobile is everything everywhere now, so it is mobile commerce. Previously we call it as e-commerce. But now the e-commerce which is done on a mobile has taken the shape of mobile commerce. So have you seen people just tapping their card and payment is being done? This is through NFC. This is through NFC, and this is technology which everyone have now. NFC, near field communication. So now your mobile will start acting as a RFID smart card, and that can interact with any reader which is nearby, and you can pay. So this is also a RFID technology, you know. I'm going to show you this sensor network. So sensor network is all about sensors which are called as the nodes, and they can gather and relay information, whatever they sense, because they are sensors, and what is happening in the physical world, wherever you are moving. Okay, these are sensors getting the information, and this can be relayed so that everyone knows what is happening. For example, your car. Now your car is a sophisticated car. It has onboard diagnostic system. Now the sensors in this car can know the location, speed, vibration, fuel efficiency, wherever it is moving. So when this all information is available from your car, it is sensing it. Now when you imagine thousands of cars are doing that. Now these are sensors or information is going back somewhere, and it can be relayed to other cars. Now you know that how Google Maps show you the red line, that where you have potholes, where you have congested roads, and even if you are a gas guzzler, that is, you are extremely using the fuel. Content provider networks. Many of the internet services now, they are coming from, or they are served from the cloud or the data center network. Now this is the picture of data center network. There are thousands and thousands and even millions of servers in a single location, and this single location go up to kilometers. So I'm talking about DC and data center network. Because of the increasing demand of computing, cloud computing. Now this is designed, this DCN is designed, the data center network, to transfer or move large amount of data between these servers which I am showing and the internet. So data center networks, this is also facing this faces certain challenges, like to scale, means to add more servers and to increase the network throughput and to have an energy efficient way of working. So before I go ahead, let me talk about network throughput, because the main network throughput challenge is cross-section bandwidth, which is actually the data rate that can be delivered between any of the two servers in this data center network. So what is the bandwidth and what is the throughput? Just understand this. See, if I give you a pipe and the water is flowing, so the mouth of the pipe is the bandwidth. If you reduce the mouth of the pipe, the bandwidth is less. But the number of, here one data packet arrives within 1 second. Here 5 data packets arrive within 1 second. So the throughput of the second one is higher. So every data center previously, they were based on very simple tree topology. We'll be talking about tree topology later in detail. But right now you can assume it to be on 3 levels. So 3 layers of switches there. Switches also, we'll be talking about. So these are just, connecting of networks, you can say. So switches, so 3 layers were there: access, distribution, or we call it as aggregate. And the third one is called core. Now the problem with this design was you cannot scale, you cannot add more servers. And most of the time the faults are there. They were subject to fault. So these are the also situations we need to know about these content provider networks, or DCN. So whenever we talk about the content provider networks or content delivery network, various popular internet services, they are delivering their content around the world, like the Googles, like the Netflix, like the Amazon Prime, using CDN, Content Delivery Network. Now this CDN is what? It is a collection of various servers, one server, second server, third server, and this is globally distributed. And how it is distributed? So that the people who are requesting it, the client who is requesting it, must get the content as early as soon as possible, or it is placed so near to them that he assumes that he is getting it from his internet service provider like this. So Google, Facebook, Netflix, Amazon Prime, etc., they operate their own content delivery networks, own CDNs they use. So content can be even a small file, or it can be even cricket match streaming video or a football match. And this has to be replicated in various locations across a single CDN. So the content has to be replicated also. That is, a copy has to be made. I'll show you what is actually happening. So this is before CDN, that is Content Delivery Network. And the second part is after CDN. Now here is the content we have. Now there is a, say, bandwidth I'm trying to show. Now the user is asking, there are user at different location, a mobile using their different location. Now what we can do after CDN is we can minimize this content and we can keep the replica of that, a kind of cache. Content cache minimizes bandwidth to origin service. Now whenever someone is asking, he will get the replica of that content near to it. For example, if someone is in Dehradun in India, he can get the server or the content from server based at Delhi rather than going to Los Angeles. So when user requests, the content delivery network will decide what replica or which server having the cache it should serve. Okay, so this procedure or this all process of CDN has to take care of the distance of the client, which server is having load, the traffic load, the congestion. So this may switch. For example, Dehradun may switch to, say, Chandigarh server rather than going to Delhi. Transit networks. Transit means if there is no direct say flight possible, then go to some other place and then take the final destination. So this is the transit. So content and application, they are hosted in DCN, data center network, and we access this content from the access network. This normally happens. Okay, see, content is there and this is in DCN. We access it through access network. There is a proper network. So content will start or traverse internet from this data center and we will have an access network and ultimately it comes to our device. Right. But when the content provider and your ISP, that is the internet service provider, for example, content provider can be Facebook, it can be YouTube. When this content provider and the actual internet company of which you are, say, subscribed to, ISP, it can be BSNL in India, for example. If the content provider and ISP are not connected directly, how do you get the data? Then we are going to rely on the transit network. So we want the relay, we have to have a transit network to carry out the traffic. Let me tell you in an easy way. There are two networks here. There is no direct path. So we have to have a transit network in between. Okay. But if the network hosting the content, for example, YouTube or Google, and the access, this network exchange is quite heavy between this access network and the content network. So what they will do, they will say, let us connect them directly. For example, the Google and Netflix, they have a direct connection between the big ISPs, internet service provider, which provides you the internet, and the large content providers. So the CDN and these ISPs are directly connected now. Okay. So traditionally, these transit networks, they were called as backbone networks. Enterprise networks. Enterprise is all about a big institution, big campus, big college, big company, big factory. So we are talking about companies and universities. They have many computers. Normally these computers are connected through a network, and this allows the employees to do certain things like sharing data, like sharing resources, like sharing information. So these resource sharing, why it is important in the organization? Okay, let me give an example. A printer. Say 50 people are there in enterprise. Would you buy 50 printers for them or just have a single printer and let them print through this? You can have a very good, very sophisticated printer, and 50 people can share this printer. Okay. And beyond that, important thing is sharing information. For example, if the enterprise is bank, the problem can be if something happens to the network, the bank will not last more than few minutes. So information sharing is also very important. In enterprise network, because the enterprise may be geographically in different area, the networks called the VPNs, or virtual private network, they will connect the individual network at different geographical notation or location or sites. For example, these are different networks. So this VPN will make them as a single logical network. We will combine this small, one is in Los Angeles, other is in Tokyo or Seoul, Mumbai. So this is an attempt to end the tyranny of geography. For example, if it is your data and you are far off, for example, 100,000 kilometers or say 100 kilometers even. Now you need to get the data because it is your data. It's your company's data or you're working on it. So this VPN is all about end the tyranny of geography. Okay. So VPN is actually making a logical network. What you can say is, in a simplest term, you have a company information system. It has some certain data or database, and this database is put in a very say heavy-end computer. You can call it as a server, and there will be some system administrator maintaining it. So employees all over the world, they have simpler machines, and they are clients, and they can access this remote data from there. Basically, the client is using the network to get the data from the server. Now, one more important part of this enterprise computer network is actually to do with people rather than information. We talked about information and resources just now. So the computer network can provide a very powerful communication medium. For example, everyone does use the electronic mail. And if the company is giving money to telephone company, it will be a waste of money. So why not to use the network to send the email? So in order to have say calls, you can have IP telephony, VoIP, voice over IP. So here you can use the internet technology over this enterprise network. And even if you want to add the video with this audio, the video with audio, the multiple employees at certain different location geographically located, they can see, they can talk, they can hold a meeting. One more thing comes here is one person is at America, the other is at India. Now they can share their screens. This is desktop sharing. They are virtually working on each other's computer. And one more goal of this enterprise business is selling and buying. It is commerce. If you talk about airlines, bookstores, their retailers, they have provided their catalogs about their goods and services online. This is how this enterprise network help to increase the level of their market. Network technology from local to global. So there are various network technologies. They are still evolving, and these can be very small and very large, even global. So the network, it can be very, very small, or it can go up to the continents and even globe. Okay. So what are these kinds of networks? What are the names? What are the technologies? We are going to discuss the network technologies that implement these networks of different sizes, different shapes, different technologies and scales. Personal area networks. As the name is suggesting, it is talking about a single human being or single entity. So the network a user or an individual is going to make, or a network corresponding or relating to a single entity. So we will call it as PAN. So PAN or personal area network lets the devices communicate, transmit, send, receive data over the range of a person. For example, here I am showing you an example, the network. Now here a computer can be connected, or a human being can have various peripheral devices, wireless headphones, keyboard, mobile, PDF, printer. All these can be these components can be connected without wires. Bluetooth is without wires. Okay, personal area can be with wires, it can be without wires. But when we are talking about technologies, we have Bluetooth. So Bluetooth is a short range wireless technology standard, and here we are talking about a fixed data is exchanging between a fixed and all the mobile devices, and these are very short distances, just you can say in meters or 2 meters, and this is using the UHF radio waves of the ISM band. This ISM band is free, right? These are short range wireless network. Without wire you can connect. So this Bluetooth is actually working using a paradigm or arrangement called master-slave arrangement. So here the system unit, a PC or the central device is a master, and all the say mouse, keyboard or headphones, etc., the peripherals are acting as a slave. So the master will direct these slaves what addresses you have to use, when to transmit, how long to transmit, and what are the frequencies to use. So this is the Bluetooth 802.15 is the standard, and Bluetooth is basically a personal area network. This comes under the category of this one. LAN or local area networks. Now LAN or local area network, this is a private network, and this can be operated in a room, in a building, in an office or home. So we are talking about a higher network than personal area network. So LANs, these are widely used because we are connecting various PCs and to share resources, exchange information. So the LANs can be wired, it can be wireless. It can be wired and wireless. So there are two examples I am showing here. One is the wireless, one is the wired LAN. So the wireless LAN system, here the computer will have a radio modem. Modem is basically modulator, demodulator, analog to digital, digital to analog, and also an antenna, because to communicate with other computers. And here each device talks to a device. Every device, that is the computing device, for example computer, is going to talk to access points, to wireless router, and to the base station. Now if you see here, there are two ways. One is the wired, the left one is wireless, the right one is wired. The left one is wireless, there is no wire in between. So a LAN can be wired, it can be non-wired. So now this system one, or a computing device or a computer, now this wants, it will not always be a computer, it can be any computing device. Now there will be a central say exchange point, and we call it as a switch. Basically it's a network device. So this is a Ethernet switch, and now this connection is like this. You go through a switch and then you connect. That is, both of the computer or the computing device will be connected to the jack of the switch, and this is how the communication will take place. So this is a switched Ethernet. What kind of Ethernet? It's because we are using a switch. Okay. Now here, this in the wireless, we have an access point. These are the different computing devices, and they are accessing it through an access point. So wireless router, access point, base station we are talking about when we are talking in terms of wireless LAN. Now the device is relaying the packet or sending the packet between the wireless computers, in between them, and also to the outer internet. Okay. There is also a mesh network configuration where the devices, the computing devices, can also send and receive packets from one another. Why I am saying that? Because in these both cases, the devices has to send it to the switch and then it should come back. That is, there is no direct connection between two devices. It has to go through switch. It has to go through access point. But in mesh network, it is possible. As I am saying, relays may be the same nodes as the endpoints. Same nodes means computing devices. Endpoints where the communication stops. Or a separate collection of nodes whose sole responsibility is relaying traffic. So the switch and access points, they have only one responsibility, to relay traffic. Now Wi-Fi is also coming in LAN. So it is a popular standard of wireless LAN. What is the IEEE number? It is 802.11. IEEE is making the protocols, it is defining the standard. So let me tell you the brief idea about this Wi-Fi. So it all started way back, but the prominent ones are 802.11a, started 54 Mbps. These are the different frequencies, mostly the frequencies which are free of the ISM band. And then we have 802.11b, 802.11g, then N, then AC, AX. You will also read somewhere AD. So all these are different flavors, different types with different speeds and working on different frequencies. Mostly if you see from 2009, it was between 2.4 gigahertz to 5 gigahertz, and the speed has gone up to 10 to 12 Gbps. Now, when we are talking about wired LANs, the transmission technologies can be different because the wire can be different. You are sending the data or the bits or the packets from one device to another. So you can use the copper, coaxial cable or optical fiber. See, the LAN has a limited size. It can only be up till a building or a home or a house. So the size are limited. When you know the boundary, you know that what will be the worst case transmission time. It is clear. If we don't know the size of the LAN, we'll know it later also, that if in advance we don't know, then we are not able to comprehend the worst case transmission time and performance and etc. The weakest link will be there. So this we'll talk later. But now, the wired LANs will always give you more speed. This is very important. Wireless will always have less speed than the wired LAN. Because it's very obvious that there is wire connected, proper transmission channel is there. When there is air in between, there are so many attenuations, so many situations arises. Okay, the wired LAN will have low latency. Latency means the time it starts and reaches the destination. There will be, the errors will be very less in the wired LANs. The throughput will be higher. Throughput means, you can say at a point how much bits can travel. Means, or how many content can travel. So we'll talk about this throughput and latency and all these in detail. But for example, for time being, the latency, the errors and the throughput, all will be, latency will be less and the errors will be less, throughput will be higher. In the wired LANs, you won't get it in the wireless LANs. Now what I'm showing right now is the IEEE 802.3. And that is called the Ethernet. We also talked about earlier who is the inventor of Ethernet. Okay, I want you to tell me. So this is called Ethernet, and this is the most common type of wired LAN. Ethernet 802.3 is the most common type of wired LAN. Okay, so I'm talking about this kind of arrangement. So this figure is showing an example of switched Ethernet topology. Here we are using a switch. So a computing device or a computer or a laptop will have a Ethernet port, and that is how we connect through this wire, Ethernet wire. So before we go ahead, let me tell you what is this switch, how does it look. This is how it looks normally. So the work of this network switch, which is actually connecting different devices or relaying the data. Now this network switch is a hardware device. We will talk about routers, we will talk about gateways. But right now, for the basic of LAN, there will be an Ethernet switch, and a network switch is networking hardware that connects devices on a computer network by using packet switching to receive and forward data to the destination devices. That is a network switch. As you see there, it is multi-port network bridge that will use the MAC, that is the address to forward data to the DLL, data link layer of the OSI layer. Okay. So we are talking about a switch. Whenever you see 802.3, that is, we are talking about a switch. So each switch is responsible for sending the data, knowing the address and sending it to the proper address. Okay. So each device speaks Ethernet protocol here, and it connects to a device which I'm showing you switch with a point-to-point link. So as I'm suggesting, this switch is relaying the packet. Packet is just a combination of bit. Okay, it has a proper format, and it sends the packet, relays the packet to the computer or computing device attached to it. and in this packet the address will be there. So the task of switch is to determine that the address of the packet is destined where to send. So the switch can have multiple ports. So if you see here, there are multiple ports, and you can connect it to the computer, and you can even compute it to another switch. In order to make a larger LAN, you can have multiple switch connected to each other, because these ports can be used to connect the computing device and even to connect the other switches. Now the question arises, what if we connect these switches in a loop? Are this network going to work? Because switch will just take the packet, send it to the destination. This is how it is done. Now we have a switch. Now we are looping it. Now where the data should go? There will be some looping of packets. But we have a solution. Very important women will be talking about her. If you know the name, just let me know. All switches now have this anti-looping algorithm. I'm giving you a hint, STP. So we are using this anti-looping algorithm here. So there will be, even if you put it or attach it in the loop, there will be no problem. So the protocol means all the rules and regulations that have been decided what path packet should travel to reach the actual destination, that is the intended computer. So it is possible to divide one large physical LANs into two smaller logical LANs. There are two things I want to highlight here. One is the looped traffic. See, this is looping, okay? Going back, coming again. So there will be a situation here, and we solve it using anti-looping algorithm. And there is one problem of flooding of traffic also. That also, there are solutions for that. But these are the general problems or challenges we face here. Now, a LAN, as I said or suggested, it can be divided into number of logical LANs. We are not physically dividing it. We are just logically dividing it. Where are the situations that arise? I'll give an example. For example, there is an institution. We have engineering department and finance department of a company. Now we would like all these are connected to a single LAN. But a single LAN won't work. We want this engineering department to be different and finance department to be different. So we can have a virtual LAN, VLAN. How will we design this? In order to do this, each port is, as I told you about the switch, so each port is tagged with a color. And now we are giving certain color to certain department. For example, we are saying that we give green for engineering and red for finance. You can choose any color, but this is the basic idea you should know. The LAN can be divided into multiple logical LANs. So the red is for finance and green is for engineering. Now switch will forward the packet accordingly. If it is destined, it is for engineering, it will go, depending upon the color, it will go to engineering only. If it is for the finance department, it will go to finance department only. So broadcast packet sent on a red port will not be received on a green port, and likewise. So this local area network, here Ethernet design broadcast all packets over a single linear cable. This is what is the design. Ethernet will always try to broadcast all packets, right? Now, this switched Ethernet, that is, we are calling it as a classic Ethernet. Whenever we are talking about Ethernet, we are calling it as a switched Ethernet or classic Ethernet. Now, it uses a very simple algorithm. The algorithm is, whenever the cable is not having any packet, the computer will transmit or the computing device will transmit. That is, whenever the cable is idle, because as I said, the normal routine is Ethernet design broadcast all packet. But this algorithm says that computer or computing device will only transmit when the cable is idle. If two or more packets, they are colliding, they will collide for sure. Okay. Now what will happen is, each computing device now have to wait. They will wait and they will try later. We will talk about CSMA, we will talk about CSMA CD. But this is just an introduction I am giving you, that we have the algorithm. This is the flowchart also I wanted to show, that both wired and wireless broadcast LANs, they can allocate different resources. It can be statically, it can be dynamically. Static dynamic, what does it mean? See, A typical static location or allocation, if you are talking about static allocation, because everyone has to send data. This is all about exchanging data. So what this static allocation will do, it will divide the time into discrete time intervals. So it will say M1 should do in this time, M2 should do in this time in round robin, M3 in this time. These are the machines in the round robin algorithm. Okay, every machine will get a stipulated time, and after that M2 will send, after this M3 will send, for M4, M5, and then if say M5, 5 machines are there, again then the M1 will send. But the problem is, when the M2 times come, M2 doesn't want to send. It has nothing to send. For example, 1 millisecond is provided to every 5 machines. It is going round robin. Every time when it comes to M2 is not ready to send. It doesn't want to send. Say M3 is also not sending. So the time that will be wasted, the static allocation wasted the channel capacity. Okay. So now we have the dynamic allocation method for a common channel. This can also be centralized. It can be decentralized also. What does it mean? Centralized means there has to be someone to guide. Decentralized means no one is there. Let me tell you again. Both wired and wireless, they can allocate the resources statically, dynamically. Static is simple round robin. Everyone is given time and their time is theirs. But it wastes the channel capacity. But the dynamic, there will be centralized, decentralized. Centralized, there will be a base station. So for example, in a cellular network, we have base station. It will decide who is going to go next. Okay. There will be some internal algorithm to decide who will be prioritizing. If this M2 should send first or M3 should send first, this is the algorithm they are going to use. This is the centralized way. And in decentralized, every machine has to decide by itself when to send, when to transmit, when not to transmit. MAN, Metropolitan Area Networks. Now metropolitan, the name is suggesting metro. We are talking about a city, a small city, big city, mediocre city. We don't know the range, but I'll tell you the kilometers. Then you can have a bit idea. Now, for example, we have a cable television networks. Now they are not very popular, but still the cable television networks. It will give you a brief idea. The MAN. In the cable television network earlier on a hill there. They used to put an antenna, and all the signals will be sent through various means to the subscriber houses who are subscribed to the cable television. But after this internet, the cable TV networks, they have started providing a two-way internet service. There are certain parts of the spectrum. There is an electromagnetic spectrum. You have to buy certain part of the spectrum, that is the frequencies. There are certain parts which are free. So the MAN, what I want to show here, how does it look? Especially when we are talking about a cable network, or how the different subscribers or the houses are connected. So we have, for example, television signal, or even say the internet. Both of the things you can understand. They are sent or fed into a centralized cable head end. And from here, it goes through different houses through the junction box. See here. What I'm trying to suggest here is that you want to access internet. You want to access cable television. Then there has to be some means through antenna or through some internet or ISPs. They use this way of head end, and then it goes to the junction box. And this junction box is specifically street, you can say. There is one more MAN. It became very popular, but it was overpowered very shortly. So that was WiMAX. WiMAX, normally people ask it, so you must know about this WiMAX, because this is also a metropolitan area network. It used to be. Now it is nowhere. There is another MAN. It was given NIEEE 802.16. So WiMAX stands for Worldwide Interoperability for Microwave Access. Let me tell you again. Worldwide Interoperability for Microwave Access. And this was based on IEEE 802.13, and it is providing higher data rates. The coverage is also higher, and this is based on MAN. So I said, and I'll tell you the kilometers, so you can have an idea about 50 kilometers for man. Wide area networks or WAN, wide area network. So the name is also suggesting that it will be a very large area. It will be a country. It can be continent, or it can even, the network can even go up to multiple continents. Multiple continents. So wide area network is the biggest one. Okay. This is the picture of a continent. It is Australia. So the WAN, it may serve as a private organization. For example, we call it as enterprise WAN. It can also be some commercial service. For example, the transit network, in-between network. Let us take an example of a wired WANs. There are proper wire being laid. So company, for example, some X company, it has some branch offices in different cities. We are talking about Australia, so it can be Perth, Melbourne and Brisbane. These are big cities and they are connected through wired WANs. Now each of these offices, they will have computers, and these computers will be called as hosts. H-O-S-T-S, host. They can do, they can have programs, running some application, connecting. So all these are called as host. Other part of this network, a WAN network, we call it as a communication subnet. These dotted lines you see, a dotted shape, it is called as a communication subnet, or we can just call it as a subnet. Now you know what is subnet and host? So this subnet has the whole responsibility of sending the data messages from different host to host. So this subnet or the communication subnet has two distinct components or parts. These are the lines, which are the transmission lines. How we are going to send the data to transmission lines. And how to send data to a particular exact intended computer or computing device. For that, we have switching elements. So we have transmission lines and switching elements. The transmission lines are basically sending the data, that is moving the bits between the machines, between the host, between the different components here in the network. And these transmission lines can be a copper wire, can use coaxial cable, optical fiber is the best, and the radio links if the wireless is adopted. And often these organizations, they are using the different telecommunication company like the Verizon, like the Geos, like the China Mobile. The switching element or switches, this is not the switch I am talking about here, this is not that switch, okay? These are switching element, we call them as switches. And these are specialized networking hardware devices that would connect two or more connection lines, because there are multiple lines coming. How to connect them? So for that, we have routers. We'll talk about that router. So when the data is coming on an incoming line, who is going to decide an outgoing line, or who is deciding where to forward them? Switching element. The switching element task is this. So here we have the router. So these switching element here in WAN, we call them as router. So in most of the WANs, wide area network, the network will contain not one, but many transmission lines, and each connecting pair of routers. So the routers will be connecting these multiple transmission lines. And if two routers, they don't have, they don't share a common transmission line, what do? They will use, or they will transmit it using another router or some transit router or in-between router. So two routers that do not share a transmission line, they do it using the other routers. Why other routers? This is how I'm trying to show how does it go. Okay, there may be many paths. There will not be one path. There will be multiple paths between two routers. How you have to send the data. Now the data can take any of the route, any of the path. So who is going to decide that? Which path has to be taken? The packets are not that intelligent. The devices have to be intelligent. The algorithm have to be made. The algorithms are there. So there are many paths, and network uses this routing algorithm to decide which path has to be used. As I am suggesting, in WAN or any kind of transmission line networking, there are routing algorithms being used because you have to send the data to proper place. So network will use the routing algorithm And the router will use what? When it gets the data, it will use the forwarding algorithm that to decide where to send the packet next. It can go to X router, it can go to Y router. So X or Y, where it has to send, the router will decide that using the forwarding algorithm. Let me give you a very brief overview of this network routing. We will be talking about Dijkstra and Bellman 4, etc. These are the routing algorithm being used. Now in this wide area network, we have virtual private networks and SD-WANs. What are these? So this picture you see is a WAN using a virtual private network. Now we don't have, say a company don't have a physical dedicated link. We don't have. How to then create a wide area network? So here VPN can be used, virtual private network, because first of all it is providing a virtualization. You will feel that you have a network, but that will be virtual. Basically you are using some other underlying backbone of some other company or some other network. That is, you are using the resources in a flexible way. That is, you are using internet connectivity for example. So with a VPN, because the internet connectivity may vary in different links, the performance will vary. You are not aware because it is not your network. If you are using virtual private network, it totally depends on what kind of internet connectivity in between we have. And this network itself, which I am talking about, this can be operated by even a single organization. It can be even operated by a commercial internet service provider or an ISP. Okay. Now I'll show you a picture here, and this shows a proper structure arrangement where it connects the WAN sites to each other. Also, it is connected to the rest of the internet. So we have a WAN. It is connected together, and it is also connected to the internet. Whenever we are talking about a satellite system, because we have to take all the arrangements into account, wired, wireless, satellite. So here we are using WAN wireless technologies. So each computer on the ground will have an antenna, and it will exchange data through get and send data via satellite. The most easiest to understand example of wide area network is this cellular telephone network. So this cellular telephone network, we are using say Verizon or say China Mobile or Jio. We are actually using the cellular telephone network. And this is also a WAN, wide area network, and it is using a wireless technology. So we have gone through various generations, and every generation has increased the speed, increased the throughput, increased the bandwidth. The first generation was only analog, there is no digital, and only you can call, voice, no digital. The second generation was digital, but for voice only. Okay. That is, you can only call. But the third generation is digital, and you can use this for voice and data both. Fourth generation is purely digital, even for voice. The first, second, third, the voice was not digital. The fourth, the voice is also digital. But when we come to the fifth generation, there is only digital. Voice on the speeds are tremendous. GB, you will talk about GBs here. Previously, in the first generation, we will talk about kbps. So in this wide area network, if we take an example of a cellular network, each cellular base station, it covers a very large area than the wireless LAN. Wireless LAN cannot compete here. So this base station are connected to each other. This is just one antenna I am showing. There are multiple base stations. They are connected through, usually wired to each other. And the data rates of the cellular network are much smaller than the wireless LAN. Wireless LAN can go up to 7, 8 Gbps and even more. But more recently, what the organization are doing, because they have distributed settlements and they need to connect sites. So they are deploying the software defined WANs, SD-WANs. Wide area network that are software defined, and they are using various different technologies. They are trying to connect this disjoint side. For example, one network with technology 1, one network with technology 2, they are combining it. How they are combining? They have some service level agreement, that is SLA, across this network. So this is now a popular thing in the wide area network. The SD-WANs These are the one of the example of SDN, that is the software defined network. And this SD-WAN, software defined WANs, this is a technology that control the network. And how does it control a network? It will use some programmable switches. They have some control logic inside this, and they will have a separate software program. Internetworks. Now, before we talk about this, you have to be very clear. There is a big subset which is the internetworks, and the internet, which you know, that is the data which you use, internet, that is just a part of it. So a collection of interconnected different networks is what we're calling as the internetwork or internet. That is not the internet I'm suggesting. This is not the global internet. It is just a specific network. There are multiple networks connected. They are called internetwork. The internet, which you know, you always hear, is just a specific internet. I hope you got the idea. Okay. So we are talking about networking. So you have to think in a bigger picture. This internet is just a part. So this internet is connecting, that is the internetwork, is to connect the content providers, the access networks, their enterprise networks, home networks. They're all connected to one another in one or the other way. Okay, which are not connected, but those are connected, forms an internetwork. So a network comprise will have a network, that is the communication network, that is the subnet, and the host. Okay, so this subnet, what this communication subnet will be there? This will be described as a network. For example, we talked about the ISP networks. An internetwork will be what? This will also be described as a network, as in the case of WAN. Okay. WAN was a proper network, wide area network. This is an internetwork. But what will be the subnet? It can be an ISP network. So the internet is basically connection of various networks. They may be independently operating and they are connected in some certain way. And that whole over the world, we call them as internetworks. Okay. So there are certain ways to connect it. How to connect them? When you are saying one technology is different, other technology is different, one is of different organization, other is of different organization, how to connect them? We use gateway. Okay. So they are networks. These are on different ways. That is, we have to connect two networks. We have to provide the network translation. These are, say, in terms of hardware and the software also. So the device that connects these two independent networks, it is called as gateway. Okay. So gateway is a network node. It is proper networking device that forms a passage or a pass or a connection between two networks. They are operating in different transmission protocols. Please understand, different protocols, and this is working in layer 3, network layer of ISO OSI layer. So these gateways are working on layer 3. So router, gateway, all they have different layers on which they work. So there are different networks. Examples of networks. Network is all about computing devices which are connected to each other, exchanging information, data. So computer networking, it has all flavors of networks. Some are very large, covering all the globe. It can be very small, like PAN, personal area network. So each network is made, constituted with different goals. Some can scale, that it can be incremented. Some cannot be. So we will look at different technologies which are there. The first, very important, is the internet. This is the best known network. Internet is nothing else. It is also a network. So what is the history? What is the evolution? How it evolved? And what are the underlying technology, the architecture of internet we are going to see? Okay. So we'll start with history, how it evolved, and finally the technology with the architectural perspective. Then you have a mobile, you might be calling as a subscriber, and then you'll be paying to a phone company. This is the mobile phone network we'll be talking about. This is also a very, prominent kind of network. And since mobile phone network is also providing the data, so we'll talk about that also. And then the IEEE 802.11 wireless LANs. You go to a hotel, you go to even the aircraft, now you get the Wi-Fi or the wireless connectivity of data. The internet. Internet is a very, very huge collection of different networks. Now these networks are talking in the same language. That is, they are using these common protocols. Protocols are nothing but the rules, regulations which are being already laid down and everyone is following it. And they are also providing certain common services. So internet is not planned by any single organization. There is no single organization which actually you can say that they have started it. And today also it is not controlled by any single organization like Cisco, like Google, like Facebook. No. It all started with the ARPANET. Now you need to understand how this ARPANET came into being. I'm talking about late 1950s. And this was the time when United States of America and USSR, these two giants or superpowers, they were involved in Cold War. Normal war is what? People fight. That is the armory actual 101 fight. But in Cold War, the countries or the parties fight, but without coming face to face. So when it was at peak, United States, that is Department of Defense, every government has a Department of Defense. So here United States DOD, they wanted to have a network that is a command and control. If something happens like a nuclear war, something happens like this, they can still be talking, they can still get connected or be connected. So this was the basic intention which all started, everything started with this. Now at this time what was happening, all the military communication, all the defense communication, they were happening on public telephone network. Normal like BSNL we have, like the different companies have different telephone, laid down backbone. So this is where this was very vulnerable. Because if you and me are talking and an army guy is also talking, it is vulnerable. We can just eavesdrop, we can blow it also, so whatever we can do. So it is vulnerable. So if you see here, this picture is showing, and you see the black dots, this is representing the telephone switching offices, and each is connected to thousands of these telephones. Basically, there were certain points, you can just assume like this, there are certain points from where different subscribers were connected. And there is a toll office, there is a switching office. So it was all in public domain. Now this was all in the national hierarchy. This was all laid down nationally in United States of America. Or these switching offices, they were connected to high level switching offices like toll offices. So it's all started with subscriber, then switching office, then we have toll office, and likewise. So it was a whole network which the Department of Defense were also using. If by chance some toll office or switching office, they were destructed or by any means, now what will happen? These all, if you see here, these are all fragmented. So one kind of destruction at one point will isolate, you can say these are the islands on islands of network. So if one is destructed, one point will not be able to talk to other point. That is the Pentagon, which was handling all the military and the Department of Defense work, will not be able to call the Los Angeles base at that time. Around 1960, DOD, Department of Defense, they gave a contract to Rand Corporation for this solution. The solution was, if something happens, we still want to be connected, because anything can happen anytime. The Pearl Harbor has happened, Hiroshima, all these, you know about the history. Now here comes an employee. He is called Paul Barron. Now he came up with a very, very fault-tolerant, highly distributed design. He said, this is my design. If something happens, if something, war or some destruction happens, then still it is quite distributed. And even if some of the, points are broken, you will still be able to talk. And this is the network he proposed. But apart from this, or you can say higher than this proposal, he gave an idea to use the digital packet switching technology. You know, this is switching office. This is switching office. So he said that since the path between any two switching office are now longer because he has made like this, the analog signal will definitely suffer attenuation. Analog signals like this, and because of the lack of energy, there will be some point when because he has the design of his has the points very distance apart. So he said there will be distortion. So he proposed that okay, we will be using the digital packet switching technology. We will be sending the packets, and these packets will be divided, and these different parts will take different paths. Any part of the packet can take any path. So there will be a disassembly. Every part will go or take any other path, and when in the receiver, all these parts of a packet will be combined again. That is in the switching technology. The concept was the data will definitely reach. Okay. Now Pentagon liked this concept of Paul Barron, but the problem was AT&T, American Telephone Telecommunication Telegraph, I guess. So this company was the telephone monopoly at that time. So United States National Telephone Monopoly it was. The Pentagon said AT&T that kindly make a prototype based on Paul Barron's idea. But AT&T at that time it was a giant. AT&T said no, this is not a good idea. We don't think it is worth making. At that time AT&T was just like the East India Company, the company which came to India and ruled for Britishers. They ruled for more than 200 years. So there was a change now. There was a paradigm shift. In October 1957, Soviet Union actually beat United States of America into space. In space. How? They actually launched the first artificial satellite called as Sputnik. So the Soviet Union, they were able to launch the satellite, and now came President Dwight Eisenhower. He said, what is happening? How this USSR has done it? So he just called the meeting, and then he came to know what is happening. Army, Navy and Air Force, they are actually backbiting. They are not doing that kind of work, or not that kind of motivated, because they were backbiting over the Pentagon's research budget. Everyone was saying, oh my God, Pentagon has so much of budget. And now came the ARPA. President said that, okay, he made a research and development organization. Now he was pointing on the research aspect. He said, we will make ARPA, that was called as Advanced Research Projects Agency. Now ARPA was just, you can say, a very small office. It has no scientists, no laboratories. It has a very small budget. So how does this ARPA work? There are different universities, there are different companies. Whosoever company or university, they have good idea, promising idea, ARPA would fund them. They would give them money. Okay, take money and do the research, and if it is worth, then we'll take it, and we'll use it for the defense use, like this. Now here comes Larry Roberts. Now he will come again and again. In 1967, he was the program manager at ARPA. And I just told you about ARPA. And he was trying to find out, he was doing everything, how to provide remote access to computers. That is, one computer is here, the other computer can be any other place, geographical location. He want to get hold of remote access. How to access another computer from one point. Okay. Now he talked to so many people. Now he also talked to Wesley Clark. Now Wesley Clark, he suggested him that you can make a packet switch subnet. And that is, subnet is basically a network. Now connecting each host to its own router. Host are computer, subnet is actually network. And router is a switching device. So he said that you can do it. You can do the remote access to computers. You can use the packet switch network, and then you can do the basic idea he gave, which is today being used also. Now Robert, he got very excited about this idea, and he started researching on it, and he actually wrote a paper. And he went to ACM SIGOPS Symposium on Operating System Principle, and this symposium was held at Gatlinburg, Tennessee. So this idea, he wrote a paper, but there was a surprise. He thought that this idea is very new and I've written a paper, and when he went there, he was surprised that this idea or this paper in this conference is already been implemented, fully implemented under the leadership of Donald Davis of NPL, National Physics Laboratory in England. And NPL was not, you cannot say it is related to defense. It was just a National Physics Laboratory campus. The different computers were connected, and this was already being implemented. And moreover, additionally, Donald Davis, they have already cited the work of Paul Barron. Remember, Paul Barron work was initially discarded by AT&T. So Robert came back from Gatlinburg and he was determined to do something to build, and that became the ARPANET. ARPANET. This was, you can say, the first internet. You can say that. Now here is a gentleman. Please look at him very carefully because we'll be talking about him. Now coming to the plan. Now Larry Roberts and others, they have a plan. The plan was the subnet. Subnet is nothing but the communication network. The subnet will consist of many computers, and these many computers will be called as IMPs. This is what you see in the picture. This will be interface message processors. And these IMPs will be connected to transmission lines, and that will be around 56 kilobit per second kbps transmission line. And because reliability was the key issue, every IMP will be connected to at least 2 other IMPs. Every interface message processor will be connected to at least 2 IMPs. It can be connected to more than that. Now each packet which will be there, will be sent across the subnet. That packet will have all the information like the size, header, checksum. Along with this, it will have a full destination address. We know it today by the IP address. Now, if this full destination address will be there, even if some IMPs are destroyed, some communication line is destroyed, the packets will still be rerouted using the alternative paths, and they will finally reach. So each node of the network will consist of what? IMP, what you see here, and a host. Host is the computer, and they will be just connected by a short wire. Okay, so this is the picture when it actually came into being. It was in 1973. This is the picture. But the basic idea was an IMP. An IMP will be connected to, that will be a part of your subnet, and every node will have IMP and a host. Host is simple computer. IMP is interface message processor. Now they decided that a host can send up to 8063 bits to its MP. Host is a computer which will be connected to IMP. So it will send up to maximum 8063 bits. And since I said this is a packet, so packet will be divided into different parts. Disassembly will be done. So that will be around 1008 bits. And this 1008 bits will be forwarded to the destination independently. So different parts are there, 1, 2, 3, you can say 8 divided by say 1008. So it will be around 8 parts of the packet. And they can take any route, any part, any destination, this routing. Each packet will be, this 1008 will be coming from different points, and it will be assembled. It will be made as 8063. Then only it will be sent to other point. So this was a kind of the store and forward packet switching network. Okay, this was the first of its kind, store and forward packet switching network. Now ARPA contracted this kind of, because they have to implement it also. In December 1968, BBN, this was a consulting firm, and it was based in Cambridge, Massachusetts, and it was awarded this contract. BBN did what? They actually used a Honeywell DDP 316 mini computers. It was having a 12K 16-bit words of magnetic core memory, and this was used as the IMP. Okay, don't worry about this 12K and 16-bit word. Just assume and just remember that they used a certain kind of mini computers as the IMPs, and there will be no inside magnetic memory, right? There will be no like hard drives we have or SSDs we have. So IMPs, they were connected by 56 kbps as planned, and they will be leased. They will be taken from the telephone companies. Now this BBN company, what they did, the software was, they made the software and it was divided into two parts, subnet and host. So what I'm trying to suggest here is, they made the software for the subnet also, which is the communication network, and the host, which will be connecting to the subnet or a communication network. They also made the software for that. Okay. So the BBN company, which was given the contract, what they did, they made or they created a software for the communication network also and the subnet also. Now what was the problem? The problem was because Larry Roberts were here. Now Larry Roberts said, I have a problem with this. The host also needs software. IMP, it's okay, I can understand. But the host also needed software. Now there was a situation. So Larry Roberts did what? He convened a meeting. He called a meeting and he called mostly the graduate students, and the place was Snowbird, Utah in the summer of 1969. Now he wanted to mitigate and solve this issue. So he called various students, and these students were young students, and these were intelligent students like IITs and ISCs we have. So graduate, they were very astounded because they asked for network expert. They asked for some grand design. But there was, for this whole network, there was no network expert, and neither there was a grand design. There was not a proper design. So these graduate kids, they have to figure out all the things on their own. So they did some experiment, and finally they were successful. And finally there were 4 nodes. This UCLA, UCSB, SRI and University of Utah, these are all universities, all start with U. So just remember, they are the different universities at that time in United States. So 4 nodes were connected. Okay. Now this gentleman, I told you about him, Len Kleinrock. He was actually the pioneer who suggested the theory of packet switching. So the first host to host, that is from one actual computer to another computer using this whole network, the first message was sent. And this was from UCLA to SRI. These are 2 universities, and he was actually involved in that, from UCLA till SRI. Now this was as the new IMPs were installed and delivered, this network grew very quickly, and it actually spanned all over United States. So now you see in just 3 years how this ARPANET grew. You see, from this A is 1969, December 1969. There are only 4 universities, 4 points, connecting points. Then we have 1970, July 1970. Then we have March 1971. Other universities like and the companies like RAND and BBN, these were all companies. They also came into being. They also became the part. Then came the April 1972. Again, the network was something like this. Then September 1972, then network was like this, and NOAA also and OAA also joined up. Finally, it grew very faster and it took a shape. This was ARPANET. ARPA also funded the research on the use of the satellite networks because they wanted this mobile packet radio networks. So they also funded this. I'll give an example. This was actually happened. There was a very famous demonstration. There was a big truck which you see here. And this was moving around California. And the communication was, this was using packet radio network to send the message to SRI. SRI is again a university. And when the message was sent to SRI, this message was sent through the ARPANET to the East Coast. And from this East Coast, these are all in United States. This was sent to University College in London through the satellite network. You know what happened? This was a famous demonstration. And this experiment was a success. People actually acclaimed it. But because of this experiment, certain new things came up. That now whatever protocols ARPANET is using, if there are different networks, they have also to be included. These protocols will not be fully competent. So we need more stout and more these are network friendly protocols. From here came the TCP/IP. So the invention of TCP/IP protocol, which is today's internet protocol, came into being. In order to encourage this TCP/IP, transmission control protocol, internet protocol, ARPA awarded various contracts, to implement this TCP/IP on various platforms. And this contract was given to giants at that time: IBM, DEC, HP, Berkeley, Unix. IBM, HP. You might be having a laptop computer of that. Now, researchers at this University of California at Berkeley, they rewrote this TCP/IP, and they use a new programming interface, and they called it as sockets. And they have a latest release of 4.2 BSD, they called them. This was, as I said, Berkeley Unix. So now they came up with the idea of using these sockets. And apart from this was just not sockets only. The new release, along with the socket, a rewriting of TCP/IP, they also made certain programs like chat program, utility program, management program. And they said it is so easy to use the sockets, and then to use all these, application programs also can be used. The TCP communication means one system will have socket, other system will have socket. We will open the socket and there will be a connection-oriented TCP connection. When this 4.2 BSD was released, it came along. Everyone adopted it. This TCP/IP sockets and various network utilities, like as I said, chat program, etc. This was a complete package. Everyone was very happy with that. And with this TCP/IP, it was easy for the LANs to connect to the ARPANET, and this grew rapidly during the mid-1970s. So this is how Internet first phase came into being. NSFNet. NSFNet is a National Science Foundation of United States. So by the late 1970s, or you can say the ending years of 1970s, everyone saw the impact and the power of ARPANET. NSF was also interested. NSF found enormous impact of this ARPANET everywhere. Okay. Now there was a catch here. ARPANET, all the universities or the institutions which are connected to ARPANET, they were only those institutions which has a contract with DoD, Department of Defense. If any other university is there, if any other institution is there, it was not connected with ARPANET. Now there was a problem. So this National Science Foundation, they said, okay, we will make a successor of ARPANET, and we will try to include most of the university research groups, or whichever university research group which wanted to join this. Late 1980s I am talking about. So what they did as initial stage, NSF created a backbone network, and they connected 6 supercomputers. Centers were there. Supercomputers means those computers which has immense power, and they were super in computing. So it was in San Diego, Boulder, Champaign, Pittsburgh, Ithaca, Princeton. And you see these points also, there are certain points I'm showing. And this was the backbone network. Now every supercomputer was provided or was connected to a fuzzball. Fuzzball is just a computer. Okay, they just gave a fancy name to it, fuzzball. So the six supercomputer were given a little brother, you can say, and it was LSI 11 microcomputer. It was called as a fuzzball. Now these fuzzball are now connected with 56 kbps lease line, and they formed a subnet. Subnet is nothing but a communication network, and they were using the same hardware technology which the ARPANET were using. I hope you got the idea. NSF tried to make a backbone, so the software technology was different. Because now the fuzzball, it started talking from the beginning in TCP/IP. So you can say NSFNet was the first TCP/IP wide area network. Transmission Control Protocol, Internet Protocol, wide area network. NSF funded now because it was a government agency, and they wanted the regional networks so that they can access any of the supercomputers, the 6 points of the backbone, and they can communicate to each other. And this network was finally called as NSFNet. You can say ARPANET was the first internet, NSFNet was the second internet. You can say like that. So it was NSFNet. And this NSFNet was also connected to ARPANET. In the CMU, Carnegie Mellon University, a fuzzball and IMP was there, and there was a link from this to ARPANET. So NSFNet was also connected to ARPANET. Right. Now here, because as I said, whenever the things are good, people will use it. The various regional networks, various universities which were not in the contract of DoD, they came up and they connected to it. So NSF net, when it came, it was a huge success, instantaneous success. So what? Because NSF was just a simple, a government company. So they gave a contract to Merit, Michigan-based Merit Consortium. And NSF also encouraged various giants like MCI, IBM, Merit to form a non-profit corporation. And it was then called as ANS, Advanced Networks and Services. And this was the first step of commercialization of the internet, today's internet. Okay. So these big companies, they formed ANS. And in 1990, this ANS, Advanced Networks and Services, it took over the NSF net and it upgraded the 1.5 Mbps line to 45 Mbps. Now ANS net is 45 Mbps. So this ARPANET, NSF net, now ANS net. After 5 years, this ANS net was sold to America Online. But at this time, everyone was into this. So there were various companies which were actually offering various IP services, commercial IP services. Now there has to be a transition. The government hand, it has to go to the private hand. So basic idea was to connect all the network, regional network, and they can communicate. For that, National Science Foundation, it awarded the contract to different network operators. And they said, okay, establish a NAP. NAP is network access points. So now there is a commercialization going on. Previously it was ANSNet, it was America Online it took, and now there was these four I am showing you. These are the different network operators. The contract was given, and these operators were Backbell, Ameritech, MFS, and Sprint. Okay. Now every network operator that wanted to provide the backbone service, because the networking part is given to the commercial or the private people. So every network operator that wanted to provide this backbone service to the NSF regional networks, they had to connect to all the NAPs, 4 of the NAPs. Okay. So what happened? Every private player, the backbone carriers you can say, they were forced to compete for the regional networks business on the basis of service and price. Everyone wanted that this regional network should connect to us. So there was a price, and this was the commercialization actually. And during the 1990s, various other countries also, they also built their own networks. Some of them were patterned or based on ARPANET and NSFNet, like the European countries. So I'm talking about different countries. They also did this. For example, EuropaNet. You see this picture, Ebone in Europe, and this all started with 2 Mbps. They upgraded it to 34 Mbps lines. And as we saw in the United States, here also the network which started with the government effort, it was also handed over to the industry, that is the private players, this network infrastructure, because there also it happened. Network infrastructure cannot be held by or cannot be handled by government player. Now here comes Tim Berners-Lee. He was the inventor of www. When then www came, internet exploded in early 1990s. Everyone was using internet. Initially at that time, it was used for email, for news groups, for remote login, for file transfer. But now the time has changed. Now we have real-time media distribution, the social media, Twitter, Facebook, these are there. Everyone is using it. And apart from that, the main traffic is coming from where? It is coming from Netflix, Amazon Prime, YouTube. All these are streaming videos platforms. The internet architecture. Now, internet is the most popular network we know. What is the architecture? That means how it is organized. What is the arrangement? This is what we are going to look at. What are the different levels? High level overview is shown here. And we'll start with the house. Just assume that you are sitting at your house and you want to connect to the internet. How does it work? How does internet architecture work? So starting with a computer at your home, this is connected to an ISP. ISP is nothing but internet service provider from where you have taken the internet and you are paying for it, right? So ISP is the internet service provider whom you pay for the services. Now once you get connected, this will allow you to exchange the packet with all other accessible hosts or the computers or the different computing device on the internet, right? So we'll see one by one. First thing is how to connect. What is the infrastructure? What is the background backbone you are going to use? There are multiple ways. The most common method for connecting to the internet from your home is using the cable television infrastructure, or you can say sending signals. So this cable network is called as hybrid fiber coaxial network. So this is already a single integrated infrastructure, and this is already using a packet based transport. And what is that packet based transport? DOCSIS. DOCSIS is data over cable service interface specification, and this is employed for variety of data services. There are the multiple data services. For example, you are watching television, high speed data and voice also. Now the device at your home and at your house is called what? It is called cable modem, and the device at the cable head end, that is the end of the cable from your house to any junction point, is called as cable head end, and this is called as CMTS because where it terminates there, cable modem termination system, CMTS, right? Let me tell you again, cable modem from your house, at your house, and CMTS at the cable modem termination system. Now here a word has come, modem. What is a modem? Modem is a short for modulator, demodulator. Mo is taken from left, dem is taken from right. Basically, it's analog to digital conversion. Telephone line is analog, computer is totally digital. So in order to send the digital data through the telephone lines, you need a conversion from digital to analog. For that, you need modem. So digital to analog is converted by modulation, demodulation, and same thing is done on the other end. Because analog is coming, you need to convert it into digital. That is done by modem. If you talk about DOCSIS, the latest standard is 3.1. This is full duplex and the data rates goes up to 10 Gbps. Okay, this is the one way cable television infrastructure. Now what are the other ways? How are you going to connect to the internet from your home? One is cable television infrastructure. The second can be FTTH, fiber to the home. That is actual laying down of the fiber cable till your home. Okay. So these are different ways. Once you are connected from your home to the ISP, now you can move packets. Okay. Now ISP is the company to which you are paying. What is point of presence? See, the location or the entry point which customer packets enter to the ISP network for service. This is ISP's point of presence. See, internet service provider or ISP has a network. The location where your packet will enter, that is your point of presence, POP. This is what I am showing, POP. See here also, these are different POPs, and this POP you are connecting from here. Here your packets will enter. After this, right now, the system is fully digital and it is packet switched. Now ISP comes in various geographical, you can say, extent. It can be regional, like a city. It can be national, it can be whole country, and it can also be international. So here we are trying to show the actual backbone and why these vertical lines are there, because this is over it. It is serving all these below it. Now their architecture, this ISP architecture, this includes long distance transmission lines, and we need some interconnection of the devices, and that are called routers at POPs. And these routers, they have help these different cities so that the ISP can serve. And this equipment or this whole scenario is called as the backbone of the ISP. Now you see here, if the packet, the destination is for a host and it is directly served by the ISP, then what will happen? We have a backbone. So the packet will be simply routed, or it will given the path and it will be delivered. Okay. If the packet destination is for a host which is also served by ISP, no problem. It will be directly served. What will happen if it is otherwise? It has to be handed over to another ISP. See, you are here. You are here. Now you are sending it to a host, and that host is also on the same ISP or served by the same ISP. The packet will be delivered. But if the case is otherwise, it has to be handed over to some other internet service provider that may not be your service provider from which you have taken the service. Right? Okay. So these are the ways this backbone works. So there are different ISPs by different companies. What is the next level? ISP connect their network. ISP have their own network, and they now connect their network to the exchange traffic in order to exchange the data and traffic to IXPs, Internet Exchange Points. The different ISPs, they are connecting through Internet Exchange Point. If you see here, we wanted to show 4 ISPs. These are all ISPs, and they are exchanging data through what? Through Internet Exchange Point. And what are there? It just has IXP already has router. Router is all about routing the data. If the ISPs are friends, that is one ISP, other ISP are friends, that is they are peer, then we will have different overlapping this area. Okay, many this connected ISPs, they are called peer with each other, with many ISPs in cities around the world, overlapping geographically. This is the overlapping area. So you need to understand only one thing. The ISP is connected, all are connected to IXP, and IXP is nothing but full of routers, a big building containing only routers, and every router is for one ISP at least. Now this IXP has a very fast optical LAN. All the routers are connected like this. And why this we have fast optical LAN? Because the packets has to be forwarded from any ISP backbone to any other. So this is a picture of Amsterdam Internet Exchange. This is one of the largest IXPs, which is Amsterdam Internet Exchange, AMS-IX. And let me tell you, more than 800 ISPs are connecting, and the data exchange is humongous. 4 terabits, it has increased every second. Imagine this. And the path of the packet, a packet takes through the internet, it depends on a peering choice. If ISPs are peer, they are friends, then it will go directly, no problem. Otherwise, it has to go through some transit network. ISP deliver directly to peer ISP. Otherwise, there has to be an in-between transit provider. So there are different ways, different paths, 2 paths. ISP, ISP peer, ISP, ISP friend, directly routing, ISP, ISP not friend. In between, you need to have a transit. There are different tiers in architecture. Tier 1, Tier 2, Tier 3. So we have in Tier 1 strong, giant transit providers. For example, AT&T, Level 3. As I'm saying, ISP, ISP, if they are not peering, they are not friends, or they don't have any tier contract, they have to go through a transit provider. So there has to be everywhere you need to have a transit. So this is the Tier 1 companies which are providing this. They are actually called Tier 1. As I said, AT&T and Level 3. They are providing the backbone network for the internet internationally. And they have thousands of routers with high bandwidth fiber optic links. Let me tell you about the companies Facebook and Netflix. These are a lot of contents providing. So they locate their servers in the data centers. So let me show you a picture here. The installation of this kind, a data center, this kind of installation is called as a server farm. Server farm. Okay. This picture you see, this is Google data center at Dallas, Oregon. And since this data center uses humongous electricity, so this data center is situated just on the bank of Columbia River, so that they can easily get cheap green electric power. This river is Columbia River. This place is Dallas, Oregon. And who owns it? Google. Okay. Now this is the actual picture. Traditional, conventionally it was, but it has changed. So let us go to the conventionally what we have learned. But I have to tell you it has changed. So we have national backbone operators. For example, a country like India, we have backbone providers. This is regional access provider like the states. So we have regional ISP. And then we have local access providers like the cities, ISP1 till ISP, whatever companies we have. And see here, there are two lines. One is the direct line, one is the dotted line. So if peering is there, you don't need a transit network. Otherwise, you need a transit network. So this is how different layers are there, different tiers are there, and this is the conventional or traditional organization of the internet architecture. But the things have changed. You know about Google, you know about Netflix, Amazon, etc. It has changed. Because over the past 10 years or decade, the hierarchy has evolved and it has flattened because of the rise of the hyper giant, the big content providers like the Googles, Netflix, Twitch, Amazon. Also the globally distributed CDNs, okay, content delivery network like the Akamai, like Limelight, Cloudflare. So just see here, the tiering and the architecture has changed because we have large content consumer hosting CDNs. Okay, a kind of tiering has changed and some flattening has been done. Mobile networks. You are using phone, you're calling also, you're using data also. So you're using mobile networks. If I talk about today, there are around 8.1 billion mobile subscription. Let me give you an idea. Indians, they are 1.38 billion. Chinese, they are 1.4 billion. Now assume these are the biggest countries, means biggest populated countries. So 8 billion mobile all over world. In 2027, it is assumed that it go up to 8.9 billion. And 92% will be for mobile broadband. Let me take you to 2018. The mobile internet traffic became more than half of global online traffic. This is the present scenario of mobile network. You see China Mobile, Jio, Airtel, China Unicom, and we have Verizon, AT&T, BSNL. Go to European countries or Mexico. But the architecture of the mobile phone network is quite different from internet, because in internet we saw that we have different tier 1 like the main transit providers like level 3 and others, tier 2 ISPs, tier 3 like this. But the architecture of mobile phone network has changed. How it is changed? The names have changed from 1G till 5G. So this picture you see is a very simplified version of the 4th generation long-term evolution architecture. We will talk about the various generation But now here we will concentrate on the present scenario. Okay. So first there is the EUTRAN. This is evolved UMTS terrestrial radio access network. Remember RAN. We'll be talking about this radio access network. The radio communication protocol that is used over the air between the mobile device. That is, this is your cell phone. Okay. This is your cell phone. And this is your cellular base station. And there is air. This is a radio communication protocol. And this is called, the base station is now called as E node B. The cellular base station we used to traditionally call, now we call them as E node B. And now the cellular phone network is no longer called, it is actually called as UMTS, Universal Mobile Telecommunication System. When 3G came, we started talking about UMTS. Now it is the formal name for the cellular phone network. And the air interface I talked about, this is based on CDMA, Code Division Multiple Access. We'll talk about this in detail. Now all this picture shows different parts. The cellular base station, along with all the controllers, this forms RAN. This RAN, Radio Access Network. Okay. You can also say that this is the wireless side of the mobile phone network. This is wireless. You know, you're talking wirelessly. And the controller node, or you can say the RNC, radio network controller, this will control how the different spectrums will be used. The base station is all about implementing the air interface. It will be implementing the air interface. The rest of the mobile network, phone network, is called the core network. What is the work? It carries the traffic for the radio access network. This is the core network. So radio access network, RNC, core network. This is the architecture. Then if you see 4G networks, the core network has now become packet switched. That is data in simple terms. And this is now called as EPC, Evolved Packet Core, EPC. The 3G UMTS core network, this has come from where? It has evolved from core network, which was used in the earliest 2G and means second generation global system mobile system. The 4G EPC, that is Evolved Packet Core, completed the transition to a fully packet switch core network. The 5G is fully digital. It's fully digital. So data services is now the most important part of phone network. When 1G came, it was all about voice. No one has thought data will come. Earlier, the GPRS systems, in the GSM systems, now it has all changed. Now, previously we used to talk about kbps speeds. Now we are talking about only GBPS speed, kilobit per second. Now it's gigabit per second. Kilo and giga has a lot of difference. Kilo is 10 to the power 3. Now the actual scenario, what happens? When the user is moving out of the range of say one cellular base station, because every cellular base station has a range. Now when it is moving from one base station to another base station, or you can say E node B to another E node B, there has to be some handover, handoff, because if some call is going or the data connection is happening, then how to be connected? So there has to be some swift and proper handover and handoff should be there, as you see in the picture. That is, in order to shift from one base station to another, what will happen? For example, you are talking to your home and you have changed the base station. So either the mobile device or the base station, because of the signal quality is dropping, both may request a handover. That, oh, okay, the signal is dropping, we need some handover. So the boundary has changed. So cell networks, which is based on the code division multiple access technology, now it is possible to connect new before disconnecting the old base station. That is, rather than disconnecting from one base station, it can connect to the next base station without disconnecting. What I am trying to say here, that the connection quality, there will be no break in service, and the mobile is actually connected for a very short while to both the base stations. Okay? One base station, the quality is low, the other will also be low, but it will peak. So this handover is called soft handover. Soft handover. The mobile is actually connected to two base stations for a short while, and there will be no break in service, and it will improve the connection quality. There is hard handover, in which the mobile has to disconnect from old base station, and then only it can connect to the new base station. This is called as hard handover. Now, how to find a mobile when there is an incoming call? This question should come into our mind. So for that, there is provision. Each mobile phone network has HSS, Home Subscriber Server, Home Subscriber Server, in the core network. And what it is doing, it knows the location of each subscriber and the profile information, that is all the authentication, authorization, name, all these scenario. So this HSS will answer this question. HSS, Home Subscriber Server. Phone companies has to take the security very seriously. First of all, you are paying to them, and they are charging. That is how they work. And any kind of payment fraud has to be taken care. So security, they have to put. This is SIM card. You are very familiar with this SIM card. But starting with the 2G GSM system, the mobile system was divided into two parts. One is your handset, and then you put a SIM card. This is a removable chip. It is an electronic chip, and it has the subscriber identity and the subscriber account information. And this chip is called as SIM card. SIM, Subscriber Identity Module. Subscriber Identity Module. Now what you do? You take one mobile, put SIM. If you take another mobile, take this SIM, put it inside another SIM, right? And this is also providing a basis for security. People can, take your mobile, but they cannot use your SIM. And with this UMTS, the mobile also uses the information of the SIM card to also check that this mobile is actually talking to a legitimate network. Along with security, there is another important consideration in mobile cellular networks, which is privacy. Now, privacy, because in wireless, this is all happening wireless. So whenever you're talking, you are actually broadcasting to everyone. So there may be some person who can eavesdrop, who can catch your signal, who can get the conversation. So in order to make this eavesdropping, the conversation to catch difficult, there are cryptographic keys on the SIM card. These are used to encrypt the transmission. Encrypt, decrypt. That is, cryptography is used here. So this is how the privacy is ensured. Packet switching and circuit switching. So the networks, there are two types of network basically, or the communication they follow. How the data flow, the routing it takes place. So it can be packet switched network, it can be circuit switched networks. And these packet and circuit, they have come from some background. Packet switch is connectionless, circuit switch is connection oriented. So in packet switching, every packet is routed independently of every other packet. So we have two messages here. They are taking different routes. Okay, for example, we have multiple routes, multiple path, multiple way. Because in between this A, B, C, D, E can be routers, it can be switch, it can be the different network devices, connections. So this message, let us assume that we have a packet. This message is a packet. Now this packet size is say 4,000. Now we divided it into say 3,000 or divided into three parts. Now there are three parts. Now the first part can take this path. It can be routed through, the other one can be routed through this path. and the other one can again take a different path. So every packet is routed. Route means the path it takes, independent of every other packet. I'm not saying that all these three will not take. They can also take a single path also. Now, what is the benefit? If this C router goes down, I showed you 2 and 3 are going. They have to go through C, or they were going through C. But now, when the system some part goes down or the router goes down, the packet switching system will dynamically reconfigure itself so that the next packet, that is, if 2 and 3 were supposed to go through C and C is down, then the packets can take different routes. That is, they can take this way or they can take this way, the other subsequent packets. Ultimately, they have to reach destination. There is one more thing here, that if too many packets, they swamp, they flood the router, it can choke the router. So what will happen? The packet will be lost. The router will be, or the networking devices will be losing or dropping the packets. This is losing of packet, and this happens in packet switching. You can call it as swamping, flooding, choking. This all results in losing of packet. This happens in packet switching. Circuit switching, it doesn't happen, right? We'll take the differences also, short way of discussing these two. So the sender will notice and resend, but the quality of service can be poor because you don't know, or there has to be some way, it has to be accounted which packet was dropped, which wasn't. So the quality of service of packet switching is not as compared to the circuit switch networks. For example, you are sending an image. Now you are sending it using packets, a message. Now the eye or knows this packet is lost. How do you see yourself at the destination? Now the other counterpart is circuit switching. It has come from telephone systems. Normally in telephone system, there are two parties. One is the caller, callee. So two parties, one calling, one attending. Now when you pick up the cradle, you dial the number, and then the other person will listen to some ring. And when he picks up the call, both of them picks up the call. Now a permanent connection is established, right? A permanent connection is established, and this is the single route I'm talking about. And this route or connection will be maintained until the call is terminated by either of these two. Now what happens when the line or the switch or the some networking devices goes down? The call will be aborted. So there is a circuit. How does this circuit form? One is calling, one is replying. So there is a kind of circuit being formed. That is why this is called circuit switching. The call has to be aborted if something goes down in between. Therefore, circuit switching is less fault tolerant than the packet switching. Okay, packet switching is all about taking different paths. Even if there is some fault, it can tolerate it. The packets can take another part, another route, right? But here, there is no other path, a single path. So circuit switching, because what is the benefit? First of all, there is a single path always established. So the quality of service, it can support easily. Because when the connection is being established, in advance. So the communication network or the subnet can reserve the bandwidth, link bandwidth. It can also, switch the buffer spaces. Also the CPU time. This all comes under the quality of service. And for example, the resources are not sufficient. If you know that there is a call already being established, then what will happen? Previously, when we used to call, 10 years back, After 11 o'clock, the calls were free. So everyone starts calling. And when we start calling, it is always busy. But once the connection is set up, the connection of circuit switching will give you a good service. So here, once you make a connection in circuit switching, the packets or the path of the route will always be the same for all the packets. There are equipments which we see today in the core network. Both are packet also and circuit switch equipment also. You know, mostly the core networks, they are still using the packet and the circuit switch equipment both. These are not different networks. The network or the communication medium, they have the same merging of this packet and circuit switched network. The older mobile phone networks, they used to have this circuit switched core network because they were carrying the voice calls. I'm talking about the 1G systems. But that legacy, that tradition is still seen in the latest 4G, 5G network UMTS. You see MSC, Mobile Switching Center, all I have tried to show here. So MSC, Mobile Switching Center, then we have GMSC, that is Gateway Mobile Switching Center. Then we will also see the Media Gateway, MGW. These are there for switch service. These are actually the circuit switched core network, like previously in PSTN, public switched telephone network, like the BSNLs we have. So still we have the combination of these two. Okay. So circuit switch is still there, packet is also there. What are the differences between a circuit switching network and the packet switching network? How the connection will be established? Circuit switching is the connection oriented. Packet switching is connection less. Packet switching is unreliable. Circuit switching is reliable. How? See, in circuit switching, when you call, there is a permanent route established. That is, the physical path between source and destination is established. So this is the physical path when you are using a circuit switching network. While you are using a packet switching network, there will be no permanent path for the packets. One packet, the other packet, they may take different route. They can take different path. The ultimate thing is they have to reach at the destination. No matter, they take the path independently. In circuit switch, if something breaks, the connection breaks. But here, in the packet switching, if some portion goes down, then also the packets will reach, they will take a different route. In circuit switching, because the permanent path is established, so we can reserve the entire bandwidth in advance, right? Because the circuit switching, we know in advance. But the packet switching, this bandwidth is not reserved. So the packets use the same path in circuit switching. They packets travel independently. And when it comes to the bandwidth, which comes under the purview of quality of service, we can reserve the entire bandwidth in advance. As I said, packet switching, we cannot reserve because different links can be established, different route can be taken for independent packets, right? Now, the other difference between circuit switching and packet switching is the bandwidth wastage. And packet switching, there is no bandwidth wastage. Bandwidth, you can think of a pipe. How much the width of the pipe is, that decides the bandwidth. So bandwidth is wasted in circuit switching, not in packet switching. In circuit switching, there is no store and forward transmission. Packet switching, it supports store and forward transmission. Now in circuit switching, once you establish a path, there is no need to store. The packets have to take the same path every time. But in packet switching, first it has to go here. Now it has to look for the path. It has to decide the route. There are routing algorithms. So if some of the link is broken, the packets may take different path. So it has to come and then it has to go. So it has the packet switching support the store and forward transmission. There are various generations of mobile telecommunication, or you can say mobile networks, or mobile services, cellular services, data services. These are different generations: 1G, 2G, 3G, 4G, 5G. So the first generation was mobile phone system only transmitting the voice calls. There was only analog signals, no digital, no bits. Now you see here AMPS, Advanced Mobile Phone System. This was deployed in United States in 1982 and it was the widely used first generation system 1G. This G stands for generation. Second generation, now it switched to transmitting voice calls in digital form. Okay, now digital came here. This was to increase the capacity, to improve the security, and then the text messaging was offered, texting. Then GSM. This GSM is actually a 2G system, global system for mobile communication, and this was deployed in 1991. 1G 1982, 2G 1991. So this is I'm showing how the phone used to look. 3G, this was initially deployed in 2001 and now it was giving both the voice and the data services digital. There's digital voice and broadband digital services. So ITU, International Telecommunication Union, they have specified 3G that if you're standing, you must get at least 2 Mbps, and if you're moving, walking, or in your train, you must get at least 384 kilobit per second. Mbps is megabit per second. This has to be the speed to call it as a 3G. And then UMTS. See, in between 2G and 3G, there is a time. So the CDMA 1 and GPRS, they all come in 2.5 G. We don't generally talk about 2.5G, but you need to know that there was 2.5G also. Some people have, they have researched on it. They have talked about it. So this UMTS is the main 3G system, which was deployed worldwide. And as we take the example of YouTube, say, there is some upload and there is some download. So this kind of thing, you can think that there is a downlink speed, 14 Mbps, uplink 6 Mbps. Now there is a spectrum, electromagnetic spectrum, and there is a radio spectrum. So radio spectrum, now for the 3G system, the spectrum or the frequency range is very scarce, is very short. Now why it is related? Because you need to talk on certain frequency. You can only talk on certain frequency. Mainly in the mobile telecommunication, you ought to use the frequency. Okay. Now this frequency or band, this is governed by the federal government. Like that is, the government has all the right. They sell it. That this is the range, and if you want to take this range, give us this money. So if you have a spectrum part, that is the licensed spectrum, so it becomes very easy to make systems and design systems according to it. Because at that particular spectrum, if you have purchased that spectrum, that is the frequency range, then you can make your own operators, design and operate the systems. But this costs a lot. This costs serious money. Let me take you to 2000. In United Kingdom, 5 3G licenses, they were auctioned by the government for $40 billion. I am talking about 2000. We are in 2022. So because of the scarcity of this spectrum, we have to do certain thing. So then came the cellular network. This cellular network has come just because of the scarcity of spectrum. There has to be done something to reuse the frequency. Okay? Because if somebody is talking and if other person is also talking, same frequency, there will be interference. And that interference, how to avoid that? So the coverage area of that base station was divided into certain cells. So if the division is such that there is a proper arrangement so that the two people talking may not interfere, or they may reuse the frequency. Okay. So within a cell, a user are assigned channels. For example, this A I am showing. All the A which you see here, they are in the same coverage area, but they do not interfere with each other and not also with the adjacent cells. These two, when they are talking, they don't interfere. So this is allowing this way of reusing or cellular network dividing into cell resulted in the frequency reuse in the neighboring cells. And this is how the capacity of the network with a same frequency was increased. So this is the latest arrangement which we use. Frequency reuse is a very important aspect in cellular network. Along with this, the usage of different kind of antennas like directional antenna, like sectored antennas on the cell towers. This also helped in reducing the interference further. So these are all the way how we use these different G systems and frequency reuse. 4G and 5G. These are the 4th generation and 5th generation system. Why we are just discussing them differently? Because now we are only talking about the data. That is, the voice is also now on data. That is the 4G, which was basically 4G LTE, which actually became popular, the long-term evolution. This LTE 4G offers faster speed. And this came up in the late 2000s. And at that time, various technologies were there. But when this 4G LTE networks, they came, for the mobile internet especially, they outspaced the WiMAX, which was 802.16. WiMAX was a very popular technique, but it was overthrown by this 4G LTE. And 5G technologies, they are promising speed of 10 Gbps. And 2020s, many countries got it, and it's still under deployment. 4G, it uses frequency bands up to 20 megahertz. But 5G, they are designed to operate in much higher frequency ranges or bands, up to 6 gigahertz. See, 20 megahertz, we are talking about 6 gigahertz. That is this 6 gigahertz, that is a high frequency. Now, what are the challenges? High frequency means a lot of attenuation, a lot of interference. Because of this, new algorithms are being made, the technology are being emancipated. That is, say, MIMO, multiple input, multiple output antenna arrays have come up. And the thing is that these short microwaves of this range of frequencies, they are easily absorbed by rain. So this is also one of the challenge which the designers are experiencing and working on. Wireless networks or Wi-Fi. Sometimes people also call it as wireless fidelity. But here the 802.11 is the IEEE. Wi-Fi is the formal name. Now Wi-Fi is using those spectrum which are unlicensed. Most of the frequencies which we see are licensed by the government, with the mobile cellular the network also use. But here the Wi-Fi is using the unlicensed band, and this has been given to ISM. ISM this for industries, as for scientific, and for medical usage, for research purposes. For these three different, because government cannot sell this to these also ISM. So ITUR has bands 902 to 928, that is for industry, and 2.4 to 2.5 gigahertz is for scientific usage. And these are free band, unlicensed band. We can use it if you are working in any of these fields. 5.725 to 5.825 gigahertz. This is for medical. So these are reserved unlicensed band. Wi-Fi is using this. So 802.11 they have clients. This can be your mobile phone, this can be your laptop, and the infrastructure, that is, we have access points, or we already know it by the name of base station. And since Wi-Fi has a range, so it is installed in a building, an area, a range, and these access points, see, the laptop and the mobile phones are wirelessly connected to access points, but these access points are connected through wire. They are wired connected. So there is a backbone of wired network. And these clients, they are talking to access points. So the systems have to go through access point, then only they can talk. But there are certain ad hoc networks like MANET, etc. If they are in same radio range, they can talk directly without an access point. This is also possible. Now, when we are dealing with the wireless networks, the frequency which we use in 802.11, these are radio signals. Now, sometimes they can be reflected off the solid objects, which is the objects which we find generally as infrastructure, the buildings, etc. And because of this, the multiple echoes of transmission, they may reach a receiver along different path. So this different path, for example, one may reinforce, two signals may reinforce, or the two signals, they are coming out of phase, so they may cancel each other. So this kind of phenomena of cancelling is called as multipath fading, and this is very natural, and most of the design issues are along this with this discussion only. So if you see here, if some reinforcement is there, you will get a non-faded signal and even higher. But if it is cancelling, the two signals are cancelling each other, you will get a faded signal. So what is the solution? Path diversity is the solution. So this has come to overcome the variable wireless condition. So we can take different multiple independent paths to send the information, not sending in one direction, but different paths. That is why it is called path diversity. And the information shall be received even if one of the path is giving you a faded signal. So the initial 1997 I'm talking about standard, this defined a wireless LAN that was running at 1 megabit per second and 2 megabit per second. And this was using frequency hopping. That is, it hops, it changes the frequency. One frequency it is working, then another frequency, then third frequency. So this was frequency hopping going on, and using the SPED spectrum. That is, the whole of the spectrum which is being assigned. Whole of the spectrum is being used. Okay, spreading the signal across the allowed spectrum. This was 1997. Now the technology emancipated. So the SPED spectrum design, it was even more extended, and it became the 802.11b standard in 1999, and the data rate increased 11 Mbps, then 802.11a, then 802.11g. These standards, there was a new modulation scheme they adopted, and we'll be talking about this OFDM, which is actually orthogonal frequency division multiplexing. And this OFDM is what? To just give you a hint, this is all about slicing. That is, it divides a wide band of spectrum into very short and very narrow slices. Over these slices, different bits are sent in parallel. So this is how the frequency selective fading is less. So this becomes less sensitive to the frequency selective fading. This is the picture I wanted to highlight. We'll be talking about this in detail. And there are different versions giving different speeds. So we have AG, AC, AD, and this AD I'm talking about because it will work only in the indoors, because it cannot penetrate the wall. Okay, so we will have the extension and the extender kind of thing. But here you see IEEE standards are there, 802.11a and 54, 11b, 11 Mbps. These are the data rates. G 54 Mbps and 600 Mbps, AC 1.3 Gbps, and then we have AX 10 to 12 Gbps. And you mark the frequency range 2.4 gigahertz until 5 gigahertz. Now, since the wireless is a broadcast medium, it goes to everyone. So 802.11 has to deal with a collision problem, because collision means two packets can collide. So in order to handle this, 802.11 also uses CSMA, carrier sense multiple access. And this CSMA, you see here, this is the classic wired Ethernet. It was used in classic wired Ethernet 802.3. And then came the Aloha. So this CSMA and Aloha, actually the collision detection and avoidance scheme is taken from them. So here, very simple algorithm, computer or the computing device wait for a short random interval before transmitting. And if someone is transmitting at that time, it will again wait for the next transmission. And this scheme really worked well in the wireless environment, Wi-Fi environment. It was not working that well in the wired networks. I'll give you a scenario here. How does it work? See, suppose this computer A is transmitting to computer B, but the range of A and C is not there. That is, the radio range of A transmitter is too short to reach computer C. Now, if C wants to transmit to B, it can listen that if someone else is transmitting. But as you see in the picture, A and C cannot talk. They don't know about each other. But if C starts transmitting, and you know already A has started transmitting, there will be collision. So once this collision happens, what will happen? C has started sending, A was already sending. Because A and C are not in range, there will be collision. What is the solution? Here, the sender will wait for a random time, and it will retransmit the packet. In Wi-Fi, there is another challenge which is called as mobility. Once you hand off, that is, if the mobile client, a mobile phone or a laptop, it is moving from the access point, it has to hand it off to the next AP, that is access point. For example, you have a house. If you go to a certain place where there is no signal, what will you do? Then you can use the extender, or you can say the booster. So the solution is that it can consist, the network 802.11 can have multiple cells with multiple APs. There is one more issue, that is the security in the broadcast wireless transmission. Because, we have we don't want it to be received by anyone else. So 802.11 standard has included, is there encryption. If you are sending AB, make it as XY. When it reaches to the sender, it can be decrypted to AB. AB is sent, making it as XY. That is the basic idea of encryption. So WEP was very popular, wired equivalence privacy. But finally, this was broken because it was the encryption technique. And then came in the 802.11i, it was replaced by Wi-Fi protected access. Initially, it was called as WPA, Wi-Fi protected access. But now it has changed to WPA2. These are the encryption techniques. There is one more, authentication also there. So in 802.1x, here we have the certificate-based authentication for the access point. Client has to take the authentication, then only will be able to access the Wi-Fi or wireless network. So mobility and security are also the issues in wireless transmission. For any network, whenever we are designing or we are trying to understand the design, there are certain aspects we need to understand. So network protocols or a network, protocol is all about the agreement between two parties, that what rules regulation they have to follow. So the design goals, first thing is reliability. That is, if some fault is there, that is, if this link is broken, then or the device has failed, the whole network should be able to recover from any kind of error, faults and failures. Second thing is resource allocation. That is sharing access to a common limited resources. Because the resources are scarce, sometimes what may happen that there are two devices, two components. One is sending the data at a fast pace. The second device is not that compatible, that is not able to take in that faster mode. So swapping can happen. Evolvability. Third thing is that the network what you make today has to be thought of future. New technologies, new techniques will come. So we have to have an incremental kind of aspect of design. Because the protocol will be there, different protocols will come, we will be able to deploy it. And the final thing comes, whenever you're dealing in public as a network, security comes. Because here, people are involved. They are good people, they are bad ones. So the network should be able to defend the network as well as the people from any kind of attack, whichever is possible. So these are certain design goals of network issues. So whenever we make a network or we try to design it or we want to learn it, understand it. So there are certain things like design goals and with the purview of protocols. Because whatever we are dealing here will be protocols, that is the agreed upon some rules and conventions and regulation. The reliability is the basic issue, and this is one of the very important issue when you are making a network. But the reliability is all about the network working correctly and recovering correctly from the failure, even if the components themselves are unreliable. The components may not be good, some of the components. For example, if we are sending packets are nothing but combination of bits. So when we are sending the packet as bits, what can happen? There's various reasons because of this. The bits may change, bit may be lost, packets may be lost. So the possibility is that there can be some electrical noise. There can be some random wireless signals because there are plenty around. There may be some hardware flaw or failure. Even the software can remove the bit or change the bit. So how do we fix? How do we find these problems and then try to recover from it or fix it? So there are two things you have to know about this. One is the error detection. One is the error correction. So these are two techniques. Error detection and correction techniques. Here we have parity codes, the checksum technique, the cyclic redundancy code, CRC we call it, and the Hamming code. So we are going to discuss all these, but for now, error detection is all about detecting the error. For example, you are sending 1011 and you got 1001. So this bit is wrong. So detection of this bit is error detection. But if you want 1011, then changing the third bit to 1, that is making it actual 1011, is the error correction. So error correction involves error detection and error correction both. So all these methods, we have to add certain redundant information. That is the actual data along with the bits so that that bit can be used for finding the errors. For example, checksum. Checksum is nothing but the XOR of all the bits. So this can be used at the destination end. There is one more issues which comes under reliability only, is how to find a path through a network. Because network means multiple paths. There will be numerous paths. How does the packet go from one place to another? So these multiple paths between the one point to another, there may be possibility that some link or routers or even the machines are broken. So the network should automatically take decision based on certain algorithm that is called as routing. Routing is all about sending the data from one place to another properly. So we have routing algorithm. It can be adaptive algorithms, non-adaptive algorithms. In adaptive, we have isolated, centralized, distributed. In non-adaptive, we can have flooding and random walk. So whenever we are dealing with network, in the design issues, resource allocation is even a greater issue. That is, when the network enlarges. For example, let us take the analogy of making a road. We make road for today traffic, but after 10 years, there will be traffic jam because we have not made this as scalable. So scalable is whenever the machines will grow, the network should also grow. The host will grow. So the people, when they increase, when the systems increase, there will be demand. So one of the way of doing this is statistical multiplexing. So this is the way of solving it. It is based on statistics of demand. Whoever wants it, just give them for certain time. That is, you see this design. This is a kind of T1, T2, T1, T2, T3. This is a round robin. Proper timing is given for every 3 machine. Okay. So this design here in statistical multiplexing, we provide or assign the bandwidth dynamically. That is, we are assigning T1, not like this, T1, T2, T3. We are not doing, when T1 is wanting, then we assign it to T1. It may happen that T2 doesn't require it. Then T3 requires it, we give it to T3. So we are not assigning it permanently, but on the basis of the demand. Okay. So basically short-term needs are catered. One more thing in the resource allocation is flow control. Because the packet is going from one place to another, one point to another, one node to another. Now, what happens if certain in a road, some accident happens. We have seen in the countries that because of this kind of traffic jam and accident, people were in jam for days. So flow control is when one sender is sending some data, some packet, and it is sending with full force. That is, maybe the throughput and the bandwidth is higher. But what about the other end? The other end which is receiving it, it may be swamped, it may be flooded, it will be overwhelmed by the number of packets. Congestion. When we have too many computers, too many nodes, or too many machines that are sending the traffic, and the network is not ready or made such that it can deliver them all. For example, for a railway reservation, for example in India, IRCTC at 11 o'clock for second class, at 12 for the air conditioned class. Previously, 4 or 5 years back, it was at 10 o'clock for both the classes. At 10 o'clock, the IRCTC website, it is a miracle if you get through it. So that is an example of congestion. So this is how we have to deal with these issues. One more aspect is the quality of service. People will only accept the product when the quality is good. For example, if cricket match is going on, who will want that a wicket is taken and you see it after say 5 minutes? Because the messages or the live commentary you are listening and you are watching something different. So real-time live video, we need the timeliness. This is the most important thing. For example, you see here in this picture, this is a regular traffic. And how this regular traffic changes into the traffic peak. This is how the things have changed. So here we have flow control, congestion, and even the quality of service is involved. So sometimes quality of service is seen like this. If we actually implement it, this is the first picture where bandwidth with no quality of service rules applied. So this is the way it will be in the actual channel. But if you apply the QoS properly, this is the channel which should be like this, an ideal channel. Evolvability. So whenever we are dealing with the design issues of networks and the protocols, when the network grows, there will be different technologies, design, everything will come. When 1G came, nobody have thought that we will be dealing with 5G. We were talking about kbps that time. Now we are talking only about gbps. So all these technologies and different things are coming. So in order to support all these, what is the if you have a big problem, how do you work with it? You try to solve it one by one, piece by piece. And you don't want to give the implementation also exposed. So the best way is to protocol layering. That is, divide the network configuration or work into different layers. So there are so many machines. There are thousands and millions of machines. So how to know about them? The idea is we have the naming service, DNS, domain name server, addressing technique, the IP addresses, all are there. So each layer needs a mechanism to identify the sender and receiver. There is one more thing. When you are sending the packet is not sent like that. Some layer has to break it. There may be some limitation on the network also. So the disassembling, transmitting and reassembling has to be done. For example, this data packet 1 is going, we have divided it into 3. Packet 2 is going like this. Packet 3 is going like this. Okay. So this is the first part, is disassembling, transmitting, and finally they have to be reassembled also. In the similar manner, the way they are sent. So this whole criteria or the concept is known as internetworking. But there are certain issues, there are certain challenges, because there are different network technologies. Some of them will not preserve the order. For example, this is 1, 2, 3. It may be, you may be getting 3, 1, 2. You don't know the sequence number. You have to have a sequence number. And every network has a limited size. There has to be known that this message, say 1 MB, for example, I'm just taking an example. The network can only send 500 KB. So you have to divide this 1 MB into 2 500 KBs. And even more, because you have to add headers, etc. One more issue is security. In the network, whenever we are saying there are thousands and millions of machines, nodes, etc. So there are chances that there are people who are not good. They will pose threats, different kind of threats. So the security is a very important aspect. For example, eavesdropping. This confidentiality deals with this kind of problems. That is, if two people are talking, why the third person has to listen? Right? There has to be some criteria or stoppage to any hacker or eavesdropper to learn what you're sending and what the other person is receiving. There has to be authentication. You have to prove that what you are. That is, prevent someone from impersonating someone else. So there has to be proper procedure and process of authentication and even authorization. For example, how do you know fake banking website from real one? I'll give you an example. That phishing attack and this fake banking, whenever you open the website, for example, say a bank, ICICI. So when you open this, you will see that first web screen will be like ICI. You will enter the username password and it will show you that you have entered the wrong password and these credentials. And this screen will go and actual screen will come there. Now the username password you have entered earlier, that will be taken by the attacker. Okay. There are other issues like there are examples also that cellular network, who is actually using the phone, the call is legitimate or not. One more thing comes here is integrity. That is, whether the message what has been sent is what is being received. That is, for example, if you are sending or debiting $100, it should not be altered to debiting say $1,000. The solution is cryptography. Cryptography is encrypting, decrypting and changing your data so that other person cannot read. I'll give you an idea. If you want to send AB and you want the destination to get AB, you can not send it as AB. You have to send it like XY. This is encryption and the other part on the destination machine will be decryption. When you combine this encryption, decryption, it will be cryptography. There are various cryptographic techniques available. Protocol layering. So this is the best idea to devise a technique to define a network using layers and protocols. So the network is quite complex, or the design can be very complex. The best way to reduce this complexity is we can divide or define the network in a proper arranged and organized manner. For example, a stack of layers we can define or levels we can define, and each one over another. For example, some party is there. You can assign food to some person. You can assign welcome to another person. For example, logistics can be given to other person. You can give some, bouquet, etc. work to some other person. So you have divided your party and given tasks to some people. Now it will reduce the complexity of your work. So this is the best way the protocol layering can help. So we need to organize in certain layers. There are different reference layer. The prominent one and the most known ones are ISO OSI layer and TCP IP layers. And please remember, they are only a reference model. One more thing you have to understand before you go to protocol layering is the number, name, contents and the function of each layer differ from network to network. That is, one network and another network, they will be having different kind of number, name, contents and function. Right? This is very important aspect. Okay. So network to network it will differ. But the whole idea is the layer concept is okay, is known. So layer is nothing but a virtual, idea being given to you. It's a virtual machine. So they are offering, every lower layer is offering some services to their upper layer. OSI reference model, TCP IP reference model. Again, let me tell you, they are reference model. That is, it is your responsibility as a network designer that you have to implement it. Now, I'll give you an example. If you have some idea about programming, especially the object-oriented programming, here the concept of object is all about hiding the data. You are making abstract data type. You are making a capsule, that is data encapsulation. You are not exposing it. So you are making a class. You will write all the variables. Then inside this class you will have functions, that is operations. So what you are doing is you are making a class, or you are hiding content, variable and function, and then again you are with different technique, that is the public private protected, you are trying to enforce the information hiding, encapsulation and object oriented programming. So the implementation is not is sometimes the framework you give, and the implementation is left over to the developer. Here in the case it is the network designer. Okay. So these layers will be discussing at stretch. In protocol layering, we have different layers, and these layers are basically based on certain concept and protocol workability and the services they are offering. For example, network layer will be I'm talking about two machines right now. So one machine say M1, so other machine say M2. Now we have say layer N. So the nth layer will be talking to the nth layer of the second machine. This is what we see, and they will be coming together for a protocol. That is, there will be rules and convention. On the basis of these rules and convention, they will talk. They will do the conversation. That is the protocol. That what will be the header size, what will we do, what is the packet size, all these. So protocol in all is an agreement between the communication parties. That is, how are we going to communicate? What are the underlying aspects? Details. I'll give an example. If a girl meets a man, there will be different scenarios. If she is a woman American lawyer, she will shake hand in a business meeting. But in if a European princess is there, or say an English princess is there, in a formal ball, you may get a kiss. So this depends on the protocol and the scenario and the situation. No American lawyer is going to kiss you for the first time. That is not a protocol. So here is a 5-layer network, and here all the dashed line you see is what you see as the actual conversation. Layer 2 is talking to layer 2. Layer 3 will only talk to layer 3 because they have some common protocol. Layer 2 will not talk to layer 3 because they don't have a common protocol. But the actual communication is not horizontal but vertical. From layer 5 it will go to 4, 3, 2, 1, and through the physical medium it will again go up in the different machine from where layer 1 to layer 2, 3, 4, 5. Okay. So the layer 2 and layer 2, they are friends because they are talking in same protocol. They are called peers. on a different machine, the same layers are called peers. These machines will be peers. Layer 4, peers. And these peers can be anything. For example, they can be software processes, a software program. It can be hardware devices. It can even be human beings, mostly in application layer. They are peers. Please remember, no data is transferred directly from layer 2 to layer 2, layer 4 to layer 4 like this. The layer end to end, it doesn't happen. Each layer will pass the data and the other information, ancillary or control information, to the layer immediately below it until it reaches the lowest layer, and finally to the physical medium. Layer 2 will give it to layer 1. Layer 5, from layer 5 it starts. Layer 4, then it goes to 3, 2, 1. Finally, it will be given for final delivery. And this below layer, which is below the layer 1, is the actual physical medium, the wires you see, the transmission media you see. Here the actual communication will take place. Right? This is the actual coaxial cable. It can be fiber, it can be transmitting of bits is happening. And the most important thing is, between each layer there will be an interface. That is, every layer junction is an interface. So this interface is most important, because this interface is defining the operation and the services and the work and the offered services from the below layer to the upper layer. That is, layer 1, 2 will tell you what layer 1 is supposed to give to layer 2. The services it is going to offer, the operation it is going to offer. So this interface makes our life very easier, because the protocol and implementation can only be changed here without even bothering about changing anything about layers. For example, communication network can go to the satellite communication. So you just have to change the interfaces. All these protocol implementation can be done in the interface layer rather than actual layer level. So when we are talking about protocol layering, it can be ISO OSI layer, it can be TCP IP layering scheme or the reference scheme. The set of layers and protocol, they all are combined and they are called as, a collection is called as network architecture. So a network architecture, whichever you do, we'll be talking about various network topology architectures, etc. So whatever you choose, or as a network designer, you ought to give, or you are supposed to give the specification of this architecture, so that the actual implementer, a person who may be writing network softwares or a person who is making a network hardware, they can make it following and obeying and conforming to all the protocols. So a set of layers and the protocols is called a network architecture. The list of protocols used by certain system, one protocol per layer, is called protocol stack. What I am trying to say here is, for example, we have a ISO OSI reference scheme we are using. Now we have 7 layers here. Every layer and one protocol in this layer. For example, the top layer, it is saying we will use HTTP. Likewise, every layer, the protocol is defined. So combination of this protocol along with this list, or one protocol per layer, this list of protocol is protocol stack. Now, how does the communication is taking place in the layering scheme or the reference models, TCP IP or the ISO OSI? Let us take a very general example. So if you see here, there are 3 layers. This is one philosopher. On the other side, there is another philosopher. These philosophers, because they are on the same layer, they are peers, they are friends. They want to talk. But one of the philosopher, he can only speak Urdu and English. The other one, he only knows Chinese and French. So there is no common language between them. So they will engage a translator, or they will hire a translator. Now these 2 translators of different philosophers, they are at layer 2. So they are peers, because their whole work is translation. Now each translator will also have a secretary. They will hire a secretary who will be actually sending the data. Now philosopher 1 wants to send a message. For example, he wants to send, I like rabbits. Ornitholagus caniculus, rabbit. Now he wants to just say, I like rabbits. This has to go to philosopher 2. How does it happen? He will pass a message because he knows only English and Urdu, so he'll write in English and it will send it across this 2-3 interface, layer 2-3 interface, to his translator. That is I like rabbits. Now the translators at level 2 or peer 2, they have already decided that we will be talking in the Dutch language. Their language spoken in Netherlands, the Holland. So they change the message into some Ikwind, Conesian, Leok like this. I may not be pronouncing it perfectly, but this is what they finally decide and they write, change. Now this choice of language is totally dependent on protocol 2 layer. They can define Hindi, they can define say any other language. Now, because they have converted it to the Dutch, now they give it to the translator, is giving it to the secretary. The secretary is sending it. Now these level 1 secretary from both the sides, they have agreed upon that they will be sending it using fax. They would have decided they will send it by say email or phone. So when the message arrives at the other secretary, because there is a proper transmission, bits transmission level. Now the secretary on the other side, philosopher 2 side, the message it gets, now it will be changed. It will be given to the translator from layer, because the philosopher has to get either in say Chinese or French. So it is the work of the translator to convert this into French. Then only this French language can be given, because the Dutch has to be converted into French. So the conversation, you can see that various parties are agreeing upon certain facts. And then finally the communication is taking place. Each protocol is independent of another, only the interfaces are changed. For example, the layer 2, they are translating. They can change it into Finnish. They can change it into say Hebrew or Arabic. It doesn't matter. Because finally, it is layer 2 to decide what language they choose. Okay. Now coming to the first layer, the secretaries, they will decide we don't want to send it by fax, we'll send it by email or telephone. So this is the agreed upon protocol between them. This is how the communication happens, and I like rabbit is transferred to philosopher 2. Now I'll show you the actual conversation, how it happens in the scenario of network protocol layering, ISO-SI layer or the TCP/IP. So here we have 5 layers, 5-layer network. Now the first layer, or the topmost layer of the left hand side, you can say the machine 1. It is sending a message called M. There is a message. Now this message, it will be sent to layer 4 of that protocol layer. So now the message at level 4, the layer 4 will add a header, say H4. So it will contain the addresses where it has to go, the sequence number if the packets are divided, all these. Okay. Now this will be sent to layer 3. Now layer 3, we have, because there may be limitation on layer 3, that this is not the size, this is the shorter size you can send. So layer 3 will divide this message M into M1 and M2, and it will add its own header, H3. So M1 and M2 will have header. See, the earlier header was placed by 4, level 4, to the actual message. So now at layer 3, there is message already, which is divided into M1 and M2. So the divided part, M1 will have the H4 header from layer 4, and one more header will be added for layer 3. And now it comes to layer 2, it will again add some header and trailer. H2 is the header, and there will be trailer. Same for message 1 and message 2. Now this will be sent to the physical machine, or the communication path. And where it goes, there will be stripping off. Trimming will go on. When it goes from layer 1 to layer 2 to layer 3, the layer 2 header work is done. So here H2 will be removed. When it goes from layer 3 to layer 4. Layer 3 has already done with the header 3. So header 3 will be removed. There will be only header 4 remain, and finally there will be combination of message M, and then it will be finally delivered to the actual layer 5 protocol peering machines. So the lower part or lower layer of protocol or lower protocols, they are normally implemented in hardware or firmware. So when you open the mobile, you see that some message will come initial to your opening. That is the firmware I'm talking about. Connections and reliability. So whenever we talk about any network, there are two things we need to discuss. First, services. The network provided services which may be connection oriented, which can be connection less. In connection oriented, there will be a proper connection established. Then only communication will take place. In connection less, there is no need to establish the path. So different layers of a reference model or different layers of a network configuration, they offer two types of service. That is, the lower layer will offer certain type of services to the upper layer just above it. So there can be two type of service. One can be connection oriented. The other one can be connectionless. What is connection oriented? See, if you have happened to know about the telephone system, one person has to call. The other person also have to, put that cradle up so that he can start the communication. That is, a connection has to get established. Then this circuit, that is one person saying, other person listening, and in the full duplex mode, this is a telephone system. So here user first has to establish a connection. Then he uses the connection, both the parties, and they release the connection. You can understand this connection oriented like a tube, for example. So here one party or one computing device, it sends or it pushes the bits. Bits, combination of bits or packet. So this is going through one end, and then the other end, what is happening? Because one is 1011 is you are sending, so 1011 will be pushed, and this will be received by a receiver. So receiver takes them out at the other end. So when this pipe or connection is established, here the sender and the receiver and the communication network, which is called the subnet also, they will have a negotiation. That is, this communication network, what will be the parameter? That is, we are sending the bit or bits or packets or messages. What will be the maximum message size? What is the quality of service required? That is the throughput, and you can say the bandwidth. So, you might have experience once you're calling on a telephone system, sometimes you don't hear, the other person repeats it. Okay. So that kind of thing are established first. So a circuit is a kind of another name for a connection. So it's a connection, proper connection between two parties. So there is a circuit involved. For example, a copper wire, etc. In the connectionless service, connection-oriented service is modeled after telephone system, the PSTN system. The connectionless service is modeled after the postal system. That is, connectionless service, just take an analogy of a postal system. You just write a letter, put it inside an envelope. On the envelope, you write the full destination address. To, from, this is your address, from is your address, to whom you are sending is your destination address. You even write the PIN code. And each of this letter is routed independently through intermediate nodes. That is, this letter, if you are writing from here to United States, it may take different countries, it may go through different postal offices. These are nodes. So you have to think this in the scenario of whole world. So packet is a message at the network layer. So there are different routes it can take, and when we talk about network layer, we'll talk about these reference models. So we have a network model there. At this point, the message is called as a packet. Okay, packet is nothing but bits. You can just understand agreed upon combination of bits. See, once you send the bit, or you can say bit stream, it will go to one node. Now assume that this is connected like this also. So some of the bits may take this route, some of the bit may take another route. So basically, depending upon the link health, the network configuration, network health, whether the link is corrected or not, what is the quality of service, then the bits will be forward. This is called store and forward switching. That is the store and forward, the message will be received and then only it will be sent. In cut flow switching, what will happen? When 1011 will come, when 1 will come, the 0 will come, 1 will be sent, then 0 will be sent. That is, whole 1011 is not received at the node, but while this message or bit stream is coming, it can be sent, it can be onward transmitted. This is cut through switching. So it is possible that the messages can be jumbled up when they receive. That is, the first message may be delayed, or it may be sent or received rather before first can come. So the sequence can change in the connectionless services. So let me again tell you, it is based on postal system, packet, it can take any route, any path. So this unreliable, which is not acknowledged, you will not get any acknowledgement. And that is why the unreliable services are faster as compared to connection oriented. So this unreliable connectionless service is called the datagram service. Datagram service. So this datagram service, this datagram word has come from telegram. Telegram. Because earlier times, telegram was sent without acknowledgement. So this is the analogy with the telegram. We will talk about the user datagram protocol, which is actually a connectionless protocol. And we have transmission control protocol, which is the connection oriented protocol. So unreliable means you don't just get the acknowledgement, and packet may be used, you don't recover it. How to recover them? But the datagram has come from telegram. Continuing with the reliability, the connection oriented and connectionless service, these are the basis of the reliability. Reliability means what? That you can rely. That is, you can have trust on that actual transmission is taking place and the transmission gets through properly. The sender will receive all the content. The reliable services, the main thing is the acknowledgement is received every time. Okay. Basically, the audio video you are using, they are not reliable service today. They are unreliable service. Why? Because in reliable services, the acknowledgement service will be there. Whatever you send, you will get an acknowledgement. For example, you are going from one place to another, you are calling your mom. So you are giving her acknowledgement. I have reached here, I have reached here. So every time in reliable service, there will be some acknowledgement always sent to the receiver. And that will be creating lot of overhead delays, because this is a proper communication from sender to receiver. Every time the acknowledgement has to come, that will add up to the overhead, the delays, the time, the effort. But the only extra effort is for the reliability. Let me give an example. File transfer, where you would like to have the reliability. If you are sending certain pages, say to print, now one page is you have sent is reached, second is not reaching. Would you be happy? No. You will need a reliable connection oriented service like for file transfer. Okay. This is very important. So this reliable connection oriented service, they have certain variation. What kind of variation they have? The reliable connection service is all about sending the acknowledgement. Every time acknowledgement will come back. But there are certain, say, flavors. One is called as message sequences. I am talking about connection oriented. You see, it is unreliable connection, reliable byte stream, and reliable message stream. So one is message sequence. Now the message sequences are nothing but the message boundaries or the packet boundaries, they are preserved. What does it mean? If you are sending, say, 1024 message, that is, if you are sending these two pages, this is first page, this is second page. Say first page is 1025 byte. And when you are sending the second page, it is 1024 byte. There are two different messages. They will be sent and received as it is, because 1024 is the message boundary and it will be preserved. You will not get in message sequence this 2048 byte message. That is, this 1024 will be combined and you will get 2048. This will never happen. These two pages will never be combined and you will get one. In message sequence, there will be proper message boundaries. As I just suggested, the pages of the book, if you are sending it to someone, say for printing or for some purpose, you would never want that the boundary should not be maintained. The second flavor of reliable connection oriented services is the byte stream. The boundaries are not defined. Connection is just stream of bytes. That is, bytes are bits only. So it is basically the digital data. If you are sending 2048 bytes, then it can be received as 2048 bytes. It can be received as two 10248 byte messages. That is, you can get as it is, or even it can be divided by the network in 1024, because it is a byte stream. It is not a message sequence. In message sequence, the message boundaries has to be preserved. In byte stream, it is not there. For example, downloading a movie, it is just a bit stream. If you are live streaming, it is just a stream of bits, right? You don't need a proper boundary here. In the reliability, there is one more flavor. That is the acknowledged datagram. I told you about the datagram. Datagram means this is a connection less. But acknowledgement means the return receipt will be there. That means there is no connection established as in the connection oriented services, but still you will get the return, which is not there in the connectionless. Connection oriented, always you will get the receipt. That is, you will get an ACK here, but there will be no proper connection. For example, text messaging on your mobile phones. So sometimes you get double take, sometimes you get, okay, the message has been delivered. While you're talking about, say you're talking on phone, digitized phone, digitized service, digitized voice traffic, sometimes you hear tin like this noise, bit of noise. This is acceptable. Okay. But if every time the acknowledgement is going, what will you hear? You will say hello and the hi will come after you have talked for say 1 minute or 2 minutes. And that is not acceptable. Okay. In video conference, for example, some pixels, if they are not seen, it is okay. But if the image is not there or the image starts rebuilding, there is a jerk, there is a, it's quite irritating. Some of the pixels you can handle or you can manage. So these are examples of certain type, acknowledged datagram, etc. And in the, about the client server scenario, there is request reply service. So here the sender will transmit a single datagram, just single datagram containing a request. And there will be one answer. The reply will be the one answer. For example, I'll give you, you want to go to the Chinese restaurant. Then you will take a mobile phone client. It will send a query to a map server. Map server is a server. This mobile phone is a client. And it will ask for a list of some nearby restaurant. And you will get a list, proper list. So this is a request reply kind of service. Service primitives. Now the name is quite, you need to understand primitive is not here a tradition or something related to history. Service primitives. The primitives here means the function, the operation, the processes. So a service, when it is related to a network, it is a function. For example, if ever you have done programming, add function, factorial function, Fibonacci function, send function, receive function. These are the functions. So the service will have number of operation it is going to offer, number of function. For example, I'm just giving example as add and fact. We'll talk about these functions. And these are available to the user processes. And whoever user process is accessing this service, the primitives or operation will be available. So if you remember the protocol stack I talked about, protocol stack is whichever reference model you are adopting all the layer will have defined protocol, one layer per protocol, that is the protocol stack. Normally when we are actually dealing it in the real scenario, this protocol stack will be in your operating system. Okay, so it will be in your laptop, it can be in your mobile, because they both have now operating systems. So the protocol stack, that is the layer of protocols, they are nothing but system calls, and these system calls are nothing but functions. So listen, connect, accept, receive, send, disconnect, these are functions. So every function is nothing but service. So primitives for the connection oriented services, they are quite different from those in the connectionless service. You'll see there is quite a similarity but differences also. Now how do we use these primitives or the services are used in actual communication? We are taking the actual example how the communication is going to take place, how the service primitives are used, service operations are used. So there are two machines here, client machine and a server machine. These are nothing but two simple machines like your machine and my machine. So how this operating system will contain a protocol stack. That protocol stack is nothing but the service primitives. And how does it work? How does this service primitive service operation which you see here on the top, these function will be applied, this will be used. So there is a proper step followed, one by one. So we are talking about a simple protocol that implements the service using the acknowledged datagram, because every time you need to get an acknowledgement, right? So we will be talking about the actual TCP and UDP's connections. Here you will know how the connection works. So this is a connection oriented communication. So you are trying to understand a communication oriented communication flavor. What will happen first? First, this server. Now server is like a shop owner. Now it has to open the shop so that the buyers can come, the customers can come. So first thing the server will do, it will execute a function called listen, so that it can show, it can indicate that I am ready to accept the incoming connections. So server will do the first thing as listen, and this is a block waiting for an incoming connection. Now when this server cannot block other systems, so it has to be suspended. What I'm trying to suggest here is this listen is implemented whenever you write this code. It is implemented by making it as a blocking system call. But now the server process will be suspended, because if the shop is open and no customer is coming, it cannot block everything. So it is suspended now. But the client is now coming. So the first client comes and it will execute a connect. So it will execute, the function connect it will use to connect to the server. Now connects function will have all the information which servers it has to connect. So there can be multiple servers. So it has to give the say IP address or the port it want to talk. So the connection or connect is the proper function, service primitive. Now what operating system is doing? The connect call, when it is established, the operating system will send a packet to its same layer peer, because it is asking for the connection. That is, a customer is coming and customer wants to enter the shop. Okay, the client process is now suspended, because if he has asked and the door is not open, it will wait. A client process will be suspended because there is no response coming from, because it is waiting for the response. Now when the client packet is sent to the server, it is received by the server, the operating system at the other end will check, okay, whether the server is in the listen mode or not. Okay, so now it will unblock the listener. As I said, the listener will be at the block state. It will unblock the listener, and the server now establishes the connection with a proper call that okay, now you can come inside my shop. So that is the accept call server will do. Server will say the accept call. Now this sends, because there will be a response every time in a connection oriented service, there will be an acknowledgement. So there will be an accept response to the client to accept connection. So connect request has gone from client to server. Server is saying okay, ready, I will accept. So accept response will come. So once the arrival of this response will come, the client will activate. It will release the client. So now client and server, they are both running and a proper connection has been established. We are discussing a proper connection oriented communication. Now server will execute a receive, because now when you go inside the shop, you have to ask for something. So the server will say, okay, tell me what do you want. Okay, server will execute a receive because it is accepting the first request. Now receive call will again block the server. The server will say, okay, what do you want? Now it goes, okay, it is now duty of clients to say what. Now client will do what? Client will now execute a send. What is the request? For example, the buyer or the customer is asking for a potato chips. So this is the request. So client send to this, execute the send to transmit its request, followed by the execution of receive to get the reply. Because it has to get the reply from the server machine also. So the request packet here unblocks the server so it can handle the request. Okay. The request packet, because now this is the request that I want the potato chips. And once the potato chips is been delivered or given to the customer, when the work is done, the server use the send to return the client, the answer to the client. Okay. This will be the send. The fourth point you are seeing, reply. So once request for potato chips is there, the potato chips will be given to the customer. Now this packet will unblock the client because it has to check whether this potato chip packet is okay or not. It will wait for some time. It will, if it is okay, when client has taken the chips packet, it will execute the disconnect because it has to terminate the connection. Say the trade is over, and it will initiate the disconnect because this initial disconnect is blocking. It will suspend the client and it will send the packet to server saying the connection is no longer needed. Now the transaction is being done. The server has to also issue the disconnect because it has to acknowledge that, okay, you are saying me to disconnect. Okay, I am also disconnect. And then both the parties, when they are disconnecting, the connection will be released. So now client get the server packet of disconnection, the client process is released and the connection is broken. The user or the customer comes out of the shop. Now the communication is over. But there may be certain things in unreliable connection. That is, there can be big messages. If a big message are sent, there will be transmission errors in the unreliable kind of communication. What are the relationship of services to the protocols? First, you have to understand what is the service, and you have to understand what is the protocol, and what is the difference and what is the similarity between them. What is the relationship between them, to be very be very clear about them. So a service is nothing but functions, primitives, operation that the lower layer provides to the upper layer. Okay, that is the layer k-1 will give some service to layer k will give some certain service to layer k+1, but it will never say how this operation or services is implemented. It will just say, I have this function, you can use it. How to use it, you decide. What about protocol? These are nothing but the rules, regulation, the convention governing the format and meaning of the packet. That is, when you send the package, what will be the size, what will be the header, what will be the trailer, because they have to be exchanged on a peer layer. So entities use this protocol in order to implement their service definition. So protocol is used when you know the protocol, then you can implement the service definition, because service is all about the operation, what operation you have to use. Now I'll give you an example of programming language. Here we have the abstract data type. In abstract data type, for example, the class will have only a function. Function is nothing but services here. Okay. Now this service, how you have to implement, it is not saying the factorial you have to implement using the direct code, or you want to call it again and again, say iterative way. So the protocol is the implementation of the service which is not visible to the user. So it's like an abstract data type. It defines the operation but not specifying the implementation. Reference models. So in a network design, the layered protocol design, that is different layers, different functions, different services, different protocols. This is a key concept. Because if any work has complexity, it is better to divide it properly so that we can handle it. And also, what is the functionality of each layer and what is the interaction between them? For example, what transport layer is going to provide to session? So what session and session layer are going to share? What will be the protocol shared? So there are two important models, TCP IP reference model and the OSI reference model. These models give you an idea that what kind of services protocols need to be used, what is the work of each layer, and how as a network designer you can implement it. The ISO OSI reference model. Now this OSI model, first let me tell you that this ISO OSI has come as a standardization, that is Open System Interconnection. This is the name of the model, and this was proposed by International Standards Organization ISO, because at that time there were so many protocols, so many things happening. It was important to standardize it so that everyone can use it in a proper way, in a arranged and say managed way. This was in 1983. In 1995 it was revised, and as I said, it was called as ISO OSI. ISO means International Standards Organization and OSI is for Open Systems Interconnection. Open Systems Interconnection. And this was called open because there were various networks which wanted to be connected to other networks. So this, for example, two networks are here, N1 and N2. They are open for the communication with other systems. So this OSI is what they should follow, these different networks. So OSI model has 7 layers. 7 layers. Now you may ask why these are 7, why they are not 6. I'll answer this. But the first layer, the topmost, is application layer. Whenever you are working on your computer or laptop, the first screen comes for any networking, that is a user interface. So application layer is providing you a user interface. Presentation is all about whatever data, information you are handling, how to present it, and even it deals with the encryption and decryption. That is, you don't want any eavesdropper or any kind of threat. So in order to handle that, presentation layer is responsible. Session layer, as the name suggests, for sessions. So you have this maintains distinction between data of separate application. If you are using two separate applications, how to maintain the distinction of data used by one and another. And it also provides dialogue control between the host. Host is nothing but the computers, different computers in the communication. This application, presentation and session, all these 3 layers have been combined in the TCP IP layer, because all the work it is doing is for user interaction. And then we have the transport layer. Transport layer is to provide the end-to-end connection. It can be reliable, it can be unreliable. So we have TCP and UDP in the another TCP IP conceptual layer. But here it is also dealing with the flow control, transport layer. Network layer, it provides the logical addressing, not the actual addressing or physical addressing. Please understand, this provides path determination using the logical addressing, not the actual addressing in the ISO OSI layer. And then we have to convert this, because every address is physical address, like the MAC address, like the IP address. So the data link layer does this thing, provides media access and physical addressing. So there is a combination of physical and the network, that is the logical addressing. Physical layer is all about transferring the data. So you are sending the bit stream, etc. So it converts digital data so that it can be sent over the physical medium. And this moves data between the different computers, hosts, or the nodes in the network. So the data starts from here, from application. Every layer adds something. And finally, through physical layer, actual wires, it can be fiber optic, it can be coaxial cable. Then it goes to the other system. And there also we have a protocol stack. So it starts from the lower layer, first layer, and it goes up to the 7th layer. Now, the question is, why these are 7 layers? What layers are doing? Why we have just 7? Why we are not having 6? Why we are not having 5? Why we are not having 100? So there are certain principles for these layers, why they were defined by ISO. So this ISO has certain principles. So the first principle is a layer created wherever different abstraction is needed. Abstraction means if you want to more exemplify it, the work of a layer, then layer is created. Each layer should perform a well-defined function. Every layer, the function of each layer has to conform, has to follow the internationally standardized protocols. And the layer boundaries is chosen such that the information flow between the interfaces. Interfaces is what? Between two layers there is interfacing. So the layer boundary is chosen such that the information flow is minimum. Then the layer decided should be not bulging or should not be thin. That is, the number of layers should be large and small enough that various function can be accommodated. One should not be overwhelmed, one should not have less function. So in OSI layer, three important concepts are there: services, interfaces, and protocol. Services are all the primitives or operation or function. The lower level will give it to the upper layer. Interface is the layer, or you can say a virtual concept between two layers that you can change anytime without changing if new technology comes. So no need to change the layer content, but just change the interfacing content if new technology, new protocols come. And protocols means two peers, that is two equal layers, they have decided upon certain rules, convention or regulation. For example, what will be the message size, what will be the header added. All these are protocols or agreed upon content before the conversation could commence. The TCP/IP reference model. TCP/IP is Transmission Control Protocol, Internet Protocol. Now this TCP/IP was not a model earlier. It was actually the protocols which was used in the grandparent of all wide area network, ARPANET. ARPANET came, then the NSFNet came, then the ANSNet came, and now we have the internet. So the grandparents, you can call it, they were also using this. So ARPANET was a research network. It was sponsored by Department of Defense, and they have connected all the major universities, government installation, and they were using PSTN, that is the leased telephone lines. Now the major idea was what? That if anything breaks in between, still the communication should commence. So when this satellite and radio communications or radio networks were also added to this underlying backbone, there was a problem in the protocols. So at that time the TCP/IP was not being used. Initially it was all different kind of protocols being used. But when different satellite radio network came in, then the TCP/IP came. So there was a new reference architecture was developed, TCP/IP reference model. And this TCP/IP reference model has come from two primary protocols that were used in earlier internet, that is the Transmission Control Protocol and Internet Protocol. These two are different protocols being used, and they were so popular because of these two primary protocols. The reference model was named as TCP/IP reference model, right? So this TCP/IP came as a standardization of other protocols which were going on the internet. It was first described by Cerf and Khan, and then it was refined and defined as a standard by Braden, and the design philosophy of this reference model was given by Clark. Now requirement of DoD, because we are discussing the first layer now, that is the data link layer. We also call it as a link layer. It is the lowermost layer of TCP/IP reference model. TCP/IP has 4 layers, because in the ISO side there were 7 layers, and the 3 uppermost layer, application, session and presentation, they were combined into 1 layer, application. So how if you compute it, it will be 4 layers because 3 layers have been combined. But there is some discussion for the lowermost layer here. I hope you got the idea. 7 layers ISO reference model. TCP/IP has 4 because 3 of the uppermost layer of ISO has been combined. Now the Department of Defense has a specific requirement that if there is any connection, if intermediate connection is broken, then still the communication should take place. So this is the requirement of Department of Defense, that is US. This has led to packet switching network, and this is based on connectionless layer. That is, if something breaks, the packet should find another way so that it reaches, the communication still take place. So there were Paul Barron, there were other people, Larry Roberts, all were involved at that time. And because of this connectionless layer, the lowest layer here, the link layer in the TCP IP, this described what links means serial lines. It can be classic Ethernet. So link layer is only defining or describing what these lines or Ethernet should do in order to meet the concept of connectionless internet layer, right? So in all, if you say this link layer is not actually a layer, it is an interface between the host or the computer and the lower transmission links, which are the actual cables through which the data will flow. I hope you got the idea. This is also the criticism of TCP IP, that link layer is actually not a layer. It is just an interface between host and transmission links, because it is just describing how the serial line and classic Ethernet should do what they should do in order to, to conform to the concept of connectionless internet layer. Coming to the second layer, that is the internet layer. This internet layer, the work and the job of internet layer is to deliver the IP, Internet Protocol IP packets where they are supposed to go to the destination. Now, in order to understand this, just think about an analogy with the snail or mail system. A person does what? He has, say, number of international letters. He wants to send internationally. So he's just dropping all these letters into a mailbox in his country. Now, most of these letters and all of the letters, for example, from Canada, now he wants to send it to India. All these letters, all of them, or one or two may not be going to the destination, otherwise all will be delivered. So now what I'm trying to suggest here is the letter are going through various international mail gateways. You never know. Not the sender, neither the receiver. They are not aware. These letters are going through international mail gateways. And each country, that is in this case each network, they have their own say stamps, envelope size, delivery rules. This is all also hidden from the users. So this internet layer is actually defining the official packet format. Packet is nothing but the combination of bits only, along with some headers, some ancillary information to support, and protocol called IP protocol. So this IP, along with this IP, there is one more companion protocol which helps IP to function, which is called the ICMP, that is Internet Control Message Protocol. Okay, this is all about messaging. Then in the TCP IP reference model, we have the transport layer. If you see here, there are two major boxes, TCP and UDP. So transport layer allows the peer entities on the source and the destination host to carry out actual conversation. So in order to have a conversation, the two end-to-end protocols, transport protocols, have been defined in this transport layer of TCP IP reference model. Because this is all about the actual conversation between the peers, that is for transport layer or application layer. So TCP and UDP. Transmission control protocol, and there is another one which is called as UDP, that is the user datagram protocol. So what is the difference? TCP is a reliable connection oriented protocol. That is, when you are using TCP, you have to establish a proper connection. Only then the byte stream can be sent and can be received. So this one machine till another machine, there has to be a connection. That is why we are calling it reliable. Reliable because every time you are getting the acknowledgement. That is, this is the bit stream I am talking about. For example, 10110111. So how to divide it? So that it segments the incoming byte stream into discrete messages. And then it passes this to the lower layer, which is the internet layer. So this byte stream has to be divided into discrete messages also. So this is dividing and sending, that is disassembling. But at the peer, that is different machine, same peer at destination, the receiving TCP processes, what does they do? They reassemble the receiving message into the output stream. So these two messages have been combined. This one message, the last bit has to go with another message, another packet, right? So TCP also handles the flow control. What is swamping? Say one machine is sending faster than the other machine receiving. So the other machine will get flooded, overwhelmed. It will get swarmed. The TCP also handles the flow control. Coming to the UDP, User Datagram Protocol. It's just the reverse of TCP, right? Because it is unreliable. Unreliable is not a bad word here. Unreliable is only that you're not getting acknowledgements every time. See? So the UDP is connectionless protocol because the data or the messages or the packet they are going through which path, the network will configure and decide. There will be no proper connection being established and no reliability, that is no acknowledgements will come. Because the problem in TCP is that there is some sequencing, flow control, that is the number of ACK will come. So there will be overhead, there will be unnecessary delay. Sometimes user wouldn't like this. So a user who wants a prompt delivery, the accuracy is not that important. For example, speech and video, speech some one tin sound or video, one frame or one say pixel goes, it will not matter. But you need a timely delivery. For that we'll use UDP. In the TCP IP reference model, the topmost layer is the application layer. The TCP IP, please note that it doesn't have a session or a presentation layers. These all three layers have actually been combined. Application layer where a user actually works. It's all about user interface and the data, how data will be presented. The application layer contains all the higher level protocols. Initially, there were some protocols, then other protocols were added. For example, initially we had Telnet, virtual terminal, file transfer protocol, FTP, and then we have electronic mail, simple mail transfer protocol. Various other protocols were added. For example, DNS, domain name system. This is for mapping the names of the host of the computer with their network addresses. That is the MAC, IP, etc. So this is DNS were added. And then we have a very popular HTTP. When Tim Berners-Lee, he created the www, World Wide Web actually, then the HTTP was introduced. And then RTP and RTCP, the protocol for delivering real-time media for voice and movies. Those who will be dealing with voice and movies, they have to learn about this RTP. So this is what the situation is. The ISO OSI layer has certain criticism. The criticism, we can divide it into the bad timing, the bad design, the bad implementation, even the bad politics. So bad timing here means the ISO OSI layer, when it came, the TCP IP was already popular. The industry and the research people, this ISO OSI protocol reference model, it got struck, it was crushed. So the industry and research and also TCP IP was already popular. So timing was bad. Then the bad technology. See, what is the criticism with respect to bad technology? This OSI model, because the protocols and the definition being given by this ISO actually, it was quite complex. It was very difficult to implement, and the operation was, even if it operates, it is very inefficient. And most of the functions like they're repeating, like addressing, flow control, error control, they are in different layers. They are reappearing again and again. Bad implementation. That is, as I said, it was complex. And the initial implementation when it came, it was very difficult. It was very huge. Even the performance issue, it was slow, unwidely. And if you compare TCP IP, this implementation was easy. So people just took it with no time. There was politics also involved. See, the TCP IP and Unix were loved by the academia, that is the university people, the research people. And the ISO OSI 7 layer, people thought, or it was being fed, that this has come from Europe. And the government of USA is trying to pressurize or put this on the head of the users here. That is why TCP IP became popular, and then this bad politics happened. The criticism of TCP IP, because TCP IP is not a perfect protocol stack, or you can say reference model. First of all, ISO-SI has clear distinction, and the key concept is service, interface, and protocol. But in this TCP IP reference model, these three were not even, they are not defined clearly, which are the backbone of any network design. And all these, all the concept cannot be proven here. For example, if you take Bluetooth, you cannot define Bluetooth protocol stack with reference to TCP IP. And the idea of the lower layer, physical or data link or network interface, host to host, many names are there. Host to network. This layer is not there. There is no physical distinction between physical and data link layer. Actually, this layer is just an interface. It just guides the links that what you have to do. That is nothing substantial this layer does. And then the TCP IP in IP and TCP. This TCP IP, these were two protocols. And they were well thought, well discussed. Everything was very proper about them. But what about the other protocols? They were just made, they were ad hoc. And these ad hoc protocols are still there in TCP IP. This was the greatest criticism. That is, you cannot have just TCP IP. What about other protocols in order for a network to work? In telecommunication world, there is standardization. That is, who is who in the telecommunication world? What are the international standards? What with respect to internet standards world? So there has to be some companies or authorities who will define and people will follow. So the topmost in the telecommunication world is ITU, International Telecommunication Union. So it has all flavor. ITU T is what we are interested in. So previously it was only in the United States. Now it is the United Nations standard. And this is telecommunication. Now coming to other international standards, we have ISO, that is International Organization for Standardization, ANSI, NIST, IEEE, I'll just show you. Then we're coming to the internet standards. We have Internet Architecture Board, IAB. Then we have the RFC, which is the request for comments, IRTF, Internet Research Task Force, IETF, Internet Engineering Task Force. So these are different authorities, standardizing authorities, working authorities. I'll just take an example of IEEE. How does it work actually? So how does it work? If you are talking about, say, Ethernet, then 802.3 is dealing with Ethernet. Wi-Fi 802.11 is going to handle. For example, WiMAX, it was there, but it flopped. So it is not there. 802.16 is not functional now. There are giant names in telecommunication world, the authorities, the organization. So first is International Telecommunication Union. In 1865 it was founded, and now it is a specialized agency of United Nations. Not only United States, it's UN. So the telecom standardization sector, ITU-T. So it is developing a lot of standards for telecommunication industry. Then we have in 1947 the ISO, International Organization for Standardization. Please see that the acronym is IOS, but it is not spoken like this. It is spoken as International Standard of International Organization for Standard, not International Standard Organization, right? So this makes industrial standards, even the management standards. In 1906, the International Electrotechnical Commission, it publishes standards for the electrical and electronic industries. Then we have ISO-IEC Joint Technical Committee. This is for IT standards. What are the metric units in the computer memory and the communication? What is the confusion? How are we going to deal with this? So capital B is for bytes, small b is for bits. In your hard drive, in your SSD, in your pen drive, when the data is stored, we talk in the power of 2. Power 2 is what? See, 2 to the power 10. This is the basic unit. that is 1024. So this is a kilobyte. A is capital, capital B is capital. So kilobyte. So 1024 byte is 1 kilobyte. 1 byte is 8 bit. Now if you increase it, that is 2 to the power 20. That is 1024 into 1024. How much this becomes? This is 1024 into 1024 is going to be 1048576 bytes. But what it will be? It will be 1 MB. 1 KB is not 10 to the power 3 bytes here. 1 KB is 1024 byte. And 1 MB is 1048576 byte. It is not 10 to the power 6 bytes in terms of storage of computer. Okay, 1 byte is, as I said, it is 8 bit. So capital B will be used for bytes, and we are talking about the memory, the storage, the computer science. Now when it comes to the network or communication, we will talk about the data rate. So data rate, this small b will come, that is b, small b is for bits. Okay, so it is not the power of 2 to the power something, but it is actually 10 to the power something. The power of 10 in computer networking speed, it is not power of 2. For example, 10 to the power 3 is 1000, and this 1000 is 1 kilobit per second. BPS is small here. Then 10 to the power 6, that is 100 into 100, that is 10 to the power 6, that is 1 megabits per second. BPS is small. Here we are talking about bits per second. Okay. Storage, we take 2 to the power 10, that is 1024 is equal to 1000 there. And in networking, it's 10 to the power, not power of 2. Okay. So this is the idea. You can take milli, and this kilo is 10 to the power 3, and then we have this kilobyte, KB, and this is 1000 bytes, this megabytes, then we have gigabyte, terabyte, petabyte, exabyte, zettabyte, and the yottabyte. Okay, this is all about the discussion of computer networks. Thank you so much. Take care of yourself.